the volume.
Yeah. So no, it's all right.
Yeah. And yeah, just unmute yourself so when you're ready.
Yeah.
Hello?
Yeah, hello there. We're just going to wait for a few people to hop on, and then we'll get started around a few minutes past 2.
So 2:05?
Yeah, 2:05.
Am I allowed to ask questions or not? Just wondering.
Yeah, you can ask questions. Yeah, because like technically we should be getting started anyway. Go for it. I'll turn my camera on, and we're just you can ask me whatever you want as we wait for people to like kind of hop in.
Okay. No, like I'm not saying now, but like let's say you say something and then but hopefully
yeah.
At the end of the seminar, am I allowed to ask questions or not?
No, that's fine. Yeah, you're free to ask questions. I'm just gonna go over some house rules like once we get started. It's kind of like on the next slide, so it's over here. But yes, you can ask questions throughout, and you can also ask questions in the middle because we're gonna have a little bit of a middle break in between this 3-hour session, and then that way you can answer further questions as well. So yeah, that's pretty much that. You can.
And another thing, you know how you said that the booklet or something or practice questions or booklet, whatever. How are you gonna get access to that?
Okay, so by the booklet, okay, I'm pretty sure I think you might be talking about this presentation itself, right?
Okay.
And I'm pretty sure it will be emailed to everyone if you've given email details.
Oh yeah, I only got the Zoom call link.
Pardon?
I only got the Zoom call link.
You've given the Zoom call link?
Yeah, but not the booklet.
Yeah. So you're gonna get the booklet after the end of the session, not before it.
Okay, thank you.
Easy. All righty. Okay, just gonna wait for.
Is everything okay?
Yeah, everything's all right.
All right, I'll leave.
Easy. All right, we're just waiting for a few people to hop on. Alrighty, I reckon we'll just get started then. I think there might be some issues with people joining with the Zoom links, so we'll get a post up for that so that they can join in case they're struggling on their end. So look, we're going to start the Year 11 chemistry course, crash course, and there's just a few housekeeping things that I want to say before we kind of run through it, because this is a crash course, right? And you can't fit an entire 3 terms worth of content in 3 hours. And still get everything done properly. We're going to do a few things to make this a bit more efficient. So we're not going to spend too much time thinking if questions are asked, okay? We're going to go through some questions, okay, not all of them, and we're going to try to go through them quickly. However, to make this more efficient and to make this useful for whoever's watching this, whoever's in the audience, right? If you know a concept and you don't feel like it's worth going through that concept and you don't feel like it's a good use of time, just message or say or unmute yourself and ask to move on, so that we can do the stuff and spend more time on things that are useful and relevant towards yourself, okay? You can ask questions throughout at any point in time, just unmute yourself and interrupt, and also in the break in between and at the end of the session as well. Apart from the times where you want to ask questions, okay, you can keep your mic muted. If you have any technical issues or you're having any problems, you can always contact the admin. The number's been put there, so you might want to take a quick picture of that number, okay, or write it down. And this way, if you need to rejoin or whatnot, we can get you back onto here as fast as possible. Now, at the end of this presentation is where the resources are going to be given. So there will be a QR code to submit your email address, and once you submit your email address to that QR code, then we can give like everything, all the slides and all other additional resources that are available. Okay, so I'll just quickly introduce myself. My name is Rikin. I'm a third-year medical student. I'm studying at Western Sydney University right now. I've been teaching at Phoenix for a few years, and chemistry I've been doing for I think 4 years now. So all of this stuff is really nice, like the back of my hand. And yeah, ask whatever you'd like. So I'm just going to move on. Okay. So yeah, and also you don't need to copy down everything. Okay, you don't need to write all of this stuff down, because once again, there will be a recording such as this one, and there will also, the slides will also be given. You can take notes only when you need it to, and attempt the examples, because as you're going to see, there's going to be a lot of examples in these slides. You can attempt them after class, so after this session. And there's also going to be a mock exam, I believe, in the resources. You can complete that under time conditions on your own. Okay, so let's begin. Properties and structure of matter. Okay, so the definitions. So here are some definitions, okay? I won't just read off the slides because that's not a proper method of teaching. What I want to ask is, from these definitions, is there anything that you don't understand so far, whoever's in the audience?
No, I understand everything.
Understand everything? Okay, it's pretty straightforward. Okay, then we won't spend too much time on it. Okay, what about these definitions?
Understand them, yeah.
Understand them, so easy peasy. Okay, separation techniques. So in terms of the separation techniques, are there any separation techniques that you're not really sure about, you don't necessarily understand? You want me to go through a little bit more?
I understand most of it.
Understand these separation techniques. Okay. Do you also understand this section over here? So when they talk about properties of separations, right? Do you understand that when they ask you questions, they're going to be utilizing most of those properties in order to differentiate them?
Not really. I'm only like mainly understand the definition of those words, like definition of the methods.
Okay. For example, okay. So what I'm asking to be clear is these properties, right? They might give you a multiple choice. They might give you a short answer question, and they might ask you, why would you distill something over evaporating it? And you've been given certain ingredients. Would you happen to know how to approach that kind of question?
Wouldn't it be if they have different boiling points? Well, different temperatures.
Different temperatures. Yeah, well, definitely different temperatures would play a role, but that still doesn't tell me why I should distill something and why I should evaporate something. Like, it doesn't tell me the difference between them. Do you get what I'm saying here?
Yes, I do.
Yeah. So just to kind of go through it a little bit, because I guess the things I want to go over in this crash course are the stuff that people ignore most of the time. So look, for chromatography, right? If your substances, okay, if they move at different rates, so if they have different molecular weights, if they have a property where their colors can be seen going across the strips of chromatography differently, and there is a clear difference, that's when you'd use it. And you'd use it if the other properties of those substances, such as the boiling point or the particle size, cannot be differentiated. So this is a technique that you use when all of these things aren't really that much different from the stuff that you're trying to separate with chromatography. For the remaining ones, okay, for example, distillation, you use distillation in a scenario where you want to separate things based off their boiling points, but you want to also keep both substances. That's the key word there. Okay, and that's what differentiates it from evaporation. Because when you evaporate something, you don't necessarily care about one of the substances. For example, if you have salt in water and you want to do gravimetric analysis of that salt in the water and you want to weigh the salt, you don't really care about the water. So you evaporate it, you know, there's a difference in the state of matter. The salt will stay solid, the water will stay liquid, and so the water will stay as a gas and it will evaporate off. Okay. Whereas in distillation, even though you're boiling things, eventually they will oscillate between being a liquid and a gas and so forth. Okay. And filtration and sieving has nothing to do with the above, has nothing to do with how they respond in a chromatography setting, has nothing to do with their boiling point or if they change from a liquid to a gas and a solid. It's simply when you have to sieve things, okay, and if you have to differentiate things between their particle size. Is that clear and straightforward?
Yes.
Yeah,
Thank you.
solid. Okay, so separating funnel, sedimentation, and centrifuging. Okay, I think these are a bit more straightforward in terms of the property of the separation because, okay, the separating funnel, it sorts by density. Sedimentation sorts by state of matter. Centrifuging states by this thing. I think what might be more relevant and useful is if we actually know examples of when these are used, okay? Or if you can give a possible example of when to use one of these techniques. So centrifuging, do you know when centrifuging might be very, very useful in a real life context?
For blood?
Yeah, blood, absolutely. And do you understand the reason that they're using centrifuging is because all of the components in blood, okay, all of them have a different like density, okay, all of them might have a different size and a shape, okay, and as a result, the things that are influenced, so the parts in the blood that are influenced by gravity the most are going to fall towards the bottom, and the parts that are not as dense are going to stay towards the top, right? That's very unique for centrifuging. What about sedimentation? Can you think of an example where sedimentation is going to be used?
No, sir, I can't think of one.
Okay, that's right. So in septic tanks, so when you have like a water processing plant and you're collecting a lot of junk water from a certain source, right? They have these large pools and they allow all of the gunk to kind of fall to the bottom. After they treat the gunk and make it heavy and whatnot, okay, they allow all of that gunk to kind of fall towards the bottom, right? And because that gunk is falling towards the bottom, that gunk is like a solid matter, and the pool of water itself is like quite pure. Like it's not pure, but it has some ions dissolved, but most of it is liquid or aqueous matter. Okay, and so because there's a clear difference in the state, so there's solids and it's being separated from the liquid in like the pool, right? That can separate with sedimentation. Okay, so if I just make a quick like drawing, for example, so let's just say you have a pool. Okay, I just bring in my whole wastewater and I want to purify it. I want to separate it. So I have a whole bunch of gunk in the pool. Okay, what's going to eventually happen, right? What's going to eventually happen is all of this gunk, okay, eventually it's going to fall towards the bottom. Okay, and because it falls towards the bottom, so I have this solid matter at the bottom, but now I have all of this pool matter. Okay, you can see I have all of this pool matter. I have all of this pool liquid aqueous solutions that I can kind of tip out. If you think about it, I can kind of separate the water by scooping it out from the sediment. And that's my separation technique. And the sole difference between this that allows me to separate it is the state of matter. The gunk is the solid and the water is the liquid. Does that make sense?
Yeah. Would it work with for example, like water and oil, or not really?
Oil and water. Okay. So oil and water, let's think about the properties of, let's think about the differences of oil and water. So oil is not dissolvable in water. Okay, neither is water in oil, and one is going to be more dense than the other. But do you see how, in terms of the state of matter, right? They're both liquid at the end of the day.
Yeah.
Yep. So look, eventually the oil and the water are going to like fall, right? They're going to fall into place. One's heavier than the other, and they'll move, right? So that sedimentation technically hypothetically would work, but it's not going to be called sedimentation because they're still both liquids at the end of the day. What that would be called is more centrifuging. Does that make sense?
Yeah, sure. Thank you.
Okay, easy peasy. All right. Okay, so let's go through the separating funnel. Let's see, properties of separation, density. Do you know what a separating funnel is?
Yeah.
Yep, okay. For those that don't, a separating funnel simply kind of looks like this. Okay, so as we just said, oil and water. So let's just say we have some oil. Let's just say we have some water. Oops. Okay, and you have a little funnel at the bottom, and you have like a little tap. Okay, and so when you have two immiscible liquids, right? Eventually the two immiscible liquids, they might come into this thing and they might be, they might be mixed up. But eventually, if you allow them to separate, okay, they'll form these two layers. Okay, there'll be liquid one here, and there'll be liquid two here. And since they organize themselves based off gravity, okay, you can kind of open this tap, you can turn it around, and you can allow all of this liquid two to kind of fall out. And then eventually, when you get close to this level, you can slow the process down and separate it that way. Okay. Alrighty, so those are your separation techniques. Okay, we're going to move on. Okay, but before we move on, was there any questions that you had on the separation technique? So this stuff over here, and also this stuff over here.
No.
No other questions. Easy peasy. Okay,
Thank you.
So once again, we're not going to go through all the examples, right? And we're only going to go through a few. Okay, just so that you get a gist of what's going to come in your preliminary exams and whatnot. So for example, example one, the most effective separation technique to separate oil from water would be, we've kind of discussed it already.
Separation funnel, B.
Separation funnel. Why? Because we're focusing on, the property of separation. This is what you want to be thinking about every time you're asked a separation technique question. Very solid. Let's go to example two. What method would you apply to separate the following mixtures?
For salt and water, wouldn't it be
Pardon?
Salt and water will be evaporation.
Yep. Next one.
Distillation.
Yep. Sand and pebbles. So think of the property that's different between them. What makes sand different to pebbles?
The density.
Yeah, density. Yeah. Anything else? Something more obvious. Easier stuff first.
I'm not too sure.
The size of the sand and the pebbles.
So would it be on separation funnel?
Okay, so remember with the separating funnel, right? You have a fixed like hole at the bottom. Okay.
Yeah.
It's like a glass tube and you have a fixed hole in the bottom. You can only really put liquid in the separating funnel. You can't really put sand and pebbles in there.
Okay.
And what would happen is,
sorry.
You go on.
No, that's fine.
Now, all I was saying is, like, if you think of it in real life as well, if you try to put sand and pebbles in there, because the funnel is fixed and small at the bottom, it's only big enough to allow liquids to pass. What's going to happen is all of those pebbles, they're going to jam the sand between them. So you wouldn't actually empty out the sand properly. Does that make sense?
Yes.
Yes. So what do you think?
Would it be sedimentation?
Okay, remember sedimentation was about state of the matter, right?
Yeah.
So if we look here, it's about state of the matter. The sand and pebbles are both solids. Does that make sense?
Yeah.
So what we'd actually end up using for sand and pebbles is this one. Okay. We would use, where is it? Here. This one. Filtration and sieving. Because what's clearly different between sand and pebbles is their particle size. Does that make sense?
Yeah.
Solid. Okay. So let's move on to example 2D, colored pigments.
Would that be centrifuging?
So the thing is, do you see how they're not really telling us anything about the colored pigments? They're not saying if they have different densities or if they have different molecular weights. They're just saying they're colored pigments. So what property do you think is the most salient with a colored pigment? It's kind of in the name.
Pigments?
Yeah, like the color. So the best method to use in this case would be chromatography, because in chromatography, different colors, they spread out differently. Does that make sense?
Not really.
Okay, so let's go back to chromatography. What that means is we don't actually understand what chromatography is. So with chromatography, okay, I'm going to explain how it's different to centrifuging. Okay. So in centrifuging, right? In centrifuging, so you have your beaker, okay, and you have your beaker being spun around at a very rapid rate, right? Okay, and then eventually the contents of that beaker is going to separate out. Now, I want you to imagine if the contents of this beaker are like ridiculously tiny, or their densities are really, really, really similar, okay, what's going to probably happen in the beaker is they're not going to separate. They're probably just going to like mix, and they're not really going to separate under centrifuging conditions. Does that make sense?
Yeah.
Yep. So, and that's the problem with colored pigment, okay? Because in colored pigment, right? Yes, the color pink, like pink dye and purple dye and blue dye, yes, they all technically have different masses, right? But that mass difference is so tiny, you're not going to see it on a centrifuge. So instead, what happens is, let's just say we have a solution of all those different colored pigments, and we put that chromatography paper over there, okay? So we put it there, and what we're going to notice is that because the colored pigments draw up against gravity, like they climb the water, they climb the chromatography strip eventually, okay? As they climb the chromatography strip, right, it's more sensitive than centrifuge, okay? But gravity still plays a bit of a role. So the dyes that are heavier, so pink, purple, these are arbitrary. I don't know if pink or purple is heavier, but let's just say pink is heavier, okay? Pink is gonna pop up here as a band, and then blue is gonna pop up here as a band because it's not as heavy, and so it can climb up the strip faster than pink can before being influenced by gravity. And then red might be like over here, right? And then that way on the chromatography strip, you can actually see it. Does that make sense?
So the lighter the color is, or the color pigment, the higher it would go?
That's right, yeah.
Okay.
Okay, easy. All right, so let's continue on. So we were up to, so we've done example 2. Okay, now example 3, this is a bit interesting. Because it's a bigger question, right? I want you guys to do this for homework and try to get it done, okay? But overall, it's just one of your gravimetric analysis questions. Do you guys feel like you're confident with this type of question?
Not really.
Not really? Oh, okay, sure. All right, let's go through this question. So a student performed the gravimetric analysis on a mixture of sand, salt, and water. A beaker that had previously been weighed, okay, contained the mixture. The student performed filtration, evaporation to separate the mixture. Results are shown below. So at the end of the day, what does the question want? The question wants us to determine the percentage by mass of each component in the mixture and show all the working out. Okay. The issue that most people have when it comes to these types of questions, right, is they just don't know what to do. As in, they see all this information, they get lost, they get confused, right? The best thing to do when you get a whole bunch of information like this is you need to visualize what's going on, right? That's the main important part. Because if you're just reading the question and you can't paint the picture of what's happening, you're going to be very, very lost. Okay. So let me paint the picture of what's happening. First of all, you have a mixture of sand, salt, and water. Okay, so I'm assuming it's in a beaker. Yep. So a beaker, yeah, it says in the second sentence. So in this beaker, you have your sand, you have your salt, and you have your water. Okay. The student performed filtration and evaporation. If you do filtration on this, you're going to separate out the what? You're going to separate out the sand from the salty water. Okay. And if you do evaporation, you're going to remove water from the salty water. Does that make sense?
Yeah.
Yep. So like I'm visualizing what's happening. I'm putting things in order in their place, and it will be much easier for me to then do a question like this, right?
Okay.
Okay. So now I know pretty much what's going on. So all of these values, they make sense. Okay. This beaker over here is 200 grams. Okay. The mass of the filter paper, I don't know why I need that yet, but if I read, I'll probably understand. The mass of the evaporating dish, I don't know why I need that yet, but I'll understand if I keep going. Mass of the beaker and mixture, that's very important because these two will link together. Okay. And if they link together, well then, yeah, if they link together, then that's going to help me understand how much the mixture weighed in the first place, right? Okay. Mass of dried filter paper and dried sand. So this is important now because now this makes sense, right? Like why did they give me the why did they give me the filter paper? Because now I can actually figure out how much the sand weighs. Okay. Oh, look, once again, another one, right? Why did they give me the evaporating dish? They gave me the evaporating dish because, oh, look, now I can figure out how much the salt weighed. Do you see how, because I imagined them all in the beginning, I now understand where everything is placed as I'm doing my maths now? Like it makes more sense. It's not just junk information.
Yeah, I see now.
Yeah. So because we know what the values are, because we know what each thing is responsible for, or what part of the maths I'm going to do it fits into, it should be very easy to figure it out. Okay. Such as I can just take a look at, the beaker. Okay. 200, I can take a look at the beaker and I can subtract it with this one and I can figure out how much the mixture weighs. So the mixture weighs 86.47 grams, right? Then I can do my subtraction with these two, filter paper and the dried sand. Okay, I can subtract those two. I can subtract these two, and then those will tell me the weight of the sand. It'll tell me the weight of the salt. I can subtract those, find the weight of the water, and then I can find them as a percentage of that, 86.47. Does that make sense?
Yeah.
Easy. All right, let's move on. So next concept is metals, non-metals, and semi-metals. So this is a nice little table over here that summarizes the main properties of metals, non-metals, and semi-metals. The way you want to interpret this table is you want to look at the properties. Okay, so these are your bread and butter for answering questions that involve this topic. So you see all of this stuff? It's a bit ugly. Let me clear that out. Okay, so you see all of this stuff, right? This is your bread and butter. You want to remember these properties when you get a short answer question or you get a multiple choice, okay? Because 80% of the time, the questions that you get asked when you have to talk about metals, non-metals, and semi-metals is you just have to talk about those properties and how they're different and how because they're different, you can now identify what is a metal, what is a non-metal, what is a semi-metal. For example, they might give you a question such as, oh, here is a compound, okay? I can't turn it into a wire. I can't bend it. When I try to bend it, it breaks, right? And it doesn't conduct electricity very, very well. It's also not very shiny, okay? And they'll give you multiple choice and they'll say, is it calcium? Is it magnesium? Is it phosphor? Or is it silicon, right? And then you have to think about those properties, match it up to this table over here that you've been given, and then it should be very straightforward. Cool?
Yeah.
Nice. All righty. So talked about that. We're going to talk about ionic compounds now. Okay. Do you have any confusions with ionic compounds?
Yeah.
Yep. Okay. Let's see. Ionic compounds, covalent compounds, polyatomic ions. Okay. And then we have some examples. All right. So ionic compounds. I guess the question is, why should we care about ionic compounds in retrospect of our prelims that are coming up? The types of questions you're probably going to get asked for an ionic compound is they're going to ask you, okay, how do you get an ionic bond, right? And how do you name this following ionic compound? And stuff like that. Those are the questions that you're going to be getting. And then how do ionic compounds dissolve in water? Those are the types of questions you probably get asked about and be given multiple choice things about as well. Okay. So now the question is, first let's go through what an ionic compound is in the first place. Okay. So if you get your periodic table, right, you'll notice that there are cations and there are anions. Do we know the difference between them?
Is a cation negative and anion positive?
So it's a good guess. It's just the other way around. Okay. The way I like to remember it is happy cat. Okay. Happy cat and angry ant. Okay. So happy cat, positive cation, angry ant, negative anion, right? But yes, essentially an ionic compound consists of cations and anions together, okay? So let's just say here is a cation, okay? And here is an anion. This is an oversimplification, okay? But these two cations and anions, there might be, two of them. There might be two negative atoms for every positive atom because the charge of the cation is just maybe perhaps stronger than the charge of the anion. But the point is you have attraction between them, okay? And that attraction is called electrostatic charge. there's no D there. Electrostatic charge. Okay. Right. That electrostatic charge is what's responsible for positive cations and negative anions to kind of attract towards each other, and then bang, you have your ionic compound. Okay, so that's the overview. If we want to understand a bit more in deep, right? If we want to get a feel for how that concept of electrostatic charge works for something that's a real example, such as magnesium iodide, okay, then we have to understand it as following. So magnesium, do you guys know in magnesium what the valency is of magnesium?
No.
Yep. If you don't, we'll quickly whip out a periodic table. Okay, you should have one ready by your side when you're doing chemistry. And then you should be able to see the valency of magnesium. You should get used to finding the valencies as well. And also do the same thing for iodide as well, please.
Uh, 12.
So the valency of which one? Sorry?
Magnesium, sorry.
Yep. Do you know what valency is, by the way? It's how many electrons you have in the outer shell. Okay, that's your valency, right? So do you know how many electrons magnesium would have in its outer shell? If not, that's okay. Could you just tell me the group that magnesium is in, please? Group meaning the column it's in. Is it in the first column, the second column from the left, and so forth?
The second column.
Second column from the left. Okay.
So it has 2 valency.
Has a valency of 2. That's absolutely correct. Okay. So magnesium is in the second column. Okay. It's going to give away 2 electrons down the track, right? And why is that? Because magnesium, okay, it has a certain number of electron shells. You said it was the number 12, so it probably has 12 electrons. Okay. But I want to focus on the last shell. So I'm not going to draw the electrons in the middle. That's why there's nothing here. I'm not going to draw the electrons in the middle. I'm just going to focus on these 2 electrons like on the outside. Okay. There's 2 electrons on the outside for magnesium. Now for iodide, for iodine, okay, I'm going to ignore all of the internal, electron shells. And I'm just going to draw the valence electron. So the valence shells, right? On that, it probably has 6 electrons. Okay, 1, 2, 3, 4, 5, 6, right? Now, we know that there's a rule of octets where all these elements, they want to be stable, okay? So what magnesium is going to do is it's going to take its electrons, this guy over here, this guy over here, it's going to donate it to iodine, okay? What ends up happening as a result of magnesium doing that, okay, is now magnesium, right? Now magnesium, okay, has full shells. So here you have your nucleus with your protons and your neutrons. And then you have your 10 electrons. So you have your 2 over here in the first shell, okay? And you have, your 8 electrons in that second shell. And there was a third shell to start off with, but it gave those 2 electrons to iodine, okay? Which has now full shells, okay? The last shell has like 8 of its electrons, right? Okay. Iodine might have more shells, I'm not entirely sure. I don't have a periodic table in front of me, but the point is, now these are both full. But remember, because it gave away 2 electrons, right? Magnesium is going to have a charge of 2+, okay, because there's 2 more protons than electrons, and iodine is going to have a charge of 2-. Can you just confirm for me if on the periodic table, iodine is in the 6th group? So that means it's not in the noble gas column, it's 2 columns away from the noble gas column. Can you confirm that for me, please?
It says 17.
Yeah, so I understand that you're unaware of what the grouping system is. So if there's 17, oh, sorry, you said there's 17 electrons. Okay. So what that means is iodine doesn't actually, okay, iodine didn't have 6 electrons in its valence shell. What iodine had, so I do apologize, what iodine had to start off with, right? What iodine had to start off with was it had 2 electrons here, it had 8 electrons here, okay? And then it had 7 in this shell. So that means we would have needed 2 iodine atoms, okay? Because there was 7 here, there was 8 here, there was 2 here, for that magnesium to give an electron to this guy and to give another of its electron to this guy over here, right? So then once the iodine gets the electron, this is negatively charged. This becomes negatively charged. Okay. So now what you end up having is you have a magnesium atom that is positively charged by 2+, and you have two of these iodines, okay, that are both negatively charged. Does that make sense, guys?
Yeah.
Yep. Cool. All right. Now, when these two cations and when these three cations and anions have these opposite charges, once again, as we said, they're going to get electrostatically attracted to each other. Because they're electrostatically attracted to each other, they're then going to form what is known as an ionic compound. Now, you can see clearly there is a bond, an ionic bond between these two structures, but don't be fooled, because just because there is a bond between these two doesn't mean that one ionic molecule looks like this. In fact, there is no such thing as an ionic molecule. The only things that exist are ionic lattices, because if magnesium is 2+ and iodine is negatively charged, if you just keep arranging them like this, and that's what happens in real life, right? Then you're going to start to get this attraction, and then eventually you're going to start to form some sort of lattice, right? Going to start to have like a 3D structure eventually. Okay. And so every time you pick up a grain of salt or you pick up a rock salt, right? What the atomic structure is on the inside is this lattice of all of these cations and anions rigidly bonded to each other in a crystalline structure. Okay. So then that brings us to ionic compounds and how to name them. Right. So there is a mistake in this slide, which is what made me make the mistake before. It should be MgI2. Okay, as you guys said. All right. How do we name ionic compounds? So first of all, you want to name the metal element first. Okay, so we discuss this guy over here. Okay, that's the metal, so magnesium. Then you want to name the non-metal, which in this case is iodine, and you want to replace the. So you know how iodine is spelled like this, iodine. You want to change it to iodide. Okay. Now, the reason that's important, the reason I'm telling you all of this in the first place is because you're going to get a whole bunch of ionic compounds. You're going to get something that looks like, for example, you might get, can someone give me a group 1 element, please? A group 1 metal. Can someone give me that?
Potassium.
Potassium, right, solid. Okay, so you have your potassium. Okay. Potassium's in group 1. Can someone give me a group 8, 7, 6, a group 5 material? So this is after the column with carbon in it. Jesse, go on. Sorry.
Phosphorus.
Is phosphorus in the column after carbon?
Yes.
Nice.
Cool.
Okay.
It's in 15th column.
Yep. Okay. So phosphorus. So potassium is going to form an ion that has a positive charge. Okay, 1 positive charge, and phosphorus is going to have one that has 3 minus. So that means you're going to need. 3 of these potassiums to balance out 1 of these phosphors. Okay. Now, can you see how there are 3 potassiums to every phosphorus? We're not going to say like tri-potassium phosphide or something like that. We're going to ignore the numbers. We're just going to name the metal. We're going to name the non-metal, and we're going to replace the ending with IDE. So it's not potassium phosphorus. It's potassium phosphide, and we don't care about the numbers or any of that in the naming system. Okay. So that's what we have to do when it comes to naming ionic compounds. We ignore the numbers, we just name the metal first, we get the non-metal, we put the IDE on the end. Cool. When it comes to covalent compounds, it's a similar thing, okay, except there's no metals in covalent compounds, right? You just have whatever is the first element and you have whatever is the second element, okay? And all you're going to be doing is you name the first elements as they are, okay? You name them as they are. You name the secondary elements as they are, and then you also add IDE at the end, but we're going to pay particular attention to the numbers. So for example, for S, there is a 1, right? It's omitted because we don't write ones, okay? But yeah, there's a 1. So the prefix for 1 is mono, and the prefix for 3 is tri, okay? Now, if there is a mono at the beginning of the first element, we just ignore it. If there was like a 2, right? If there was a 2, you know, say there was a 2 here, okay, and then the prefix would be di, then we would say something like we would say di, sulfur, and then the rest of the molecule. But because in this example, okay, there is mono, okay, we just ignore it for the sulfur, but there is 3. Okay, there is a 3, and the prefix for that is tri. So then we name the first one with the prefix, unless it's a mono, and then we name the second one with the prefix, add IDE, and yeah, add the prefix as well. So this ends up becoming sulfur trioxide. Sulfur, tri, the prefix, oxygen, IDE for the end. Does that make sense, guys? There's not that many of you. Please don't be shy. Just say yay or nay. Okay. So that way I can move through things quickly. And that way I know if the things are relevant for you guys or not. Cool, cool.
Okay.
Cool. Alrighty. Polyatomic ions. Does anyone here struggle with polyatomic ions? If you don't want to unmute yourself and say anything, you can just like pop it into the chat. And I have the chat next to me and I can, you know, see your messages. Is there anything confusing about polyatomic ions that you want me to go over or you don't understand? Or are we good to kind of move past it? I'm okay with okay. Thanks, Jesse. Alrighty. Gabriel, would you like to go over polyatomic ions or anything about
them? Yes, please.
What about polyatomic ions are you confused about? Hello? Gabriel, we're waiting for you.
Oh, sorry. It's fine. Sorry. All right.
All good. So you understand polyatomic ions? There's no issues or anything?
No issues.
Okay. For those in the audience that have no idea what a polyatomic ion is or is very confused, because I remember when I was in year 10, I know this is year 11 course, but in year 10, I was exposed to this first and I was extremely confused. The way I want you guys to understand these is, at the end of the day, these are just covalent compounds that have a charge. Yes, I'm saying covalent, right? Because, okay, if we think about it, right? Let's just say we get hydroxide, okay? If we get a hydroxide, it's an O and it's a H, and somehow it has a negative charge. Doesn't really make a lot of sense. Actually, OH might make sense, but let's say, for example, sulfate, okay? S and then 4 of these O's, okay, and it has a charge of, what was it, charge of 2 minus, okay? Okay, it doesn't make sense. Sulfur, the valency of sulfur and the valency of oxygen, if you add them together, it's nowhere near the number 2 minus, right? And that's because they're sharing electrons of some sort, okay? And they share it in this manner so that at the end of the day, overall, there are just 2 more electrons than there are the number of protons in the sulfur and the 4 oxygens, okay? So all of these thingies, all of these polyatomic ions are covalently bonded. That one, that one, that one, that one, everything, they're all covalently bonded, but they have a charge. And because they have a charge, you can plug them onto other cations and anions. So they act like an ionic compound, but they're actually a covalently bonded substance, okay? Now, some quick examples. So speed through these examples. I want you guys to have a go at answering A, please. Okay. And if you're confused and you don't really know how to name the compounds, first ask yourself, okay, is this an ionic compound or is this a covalent compound? And how do I figure that out? Is there a metal and a non-metal, or is it just non-metal and non-metal? Jesse, what do you think it is?
For the first one?
Yeah, example 1A, yes.
It's a covalent.
Covalent, solid. So how would we go about naming this?
You look at the number and then use the prefix. So it's phosphorus trichloride.
Bang, absolutely solid. Okay, Gabe, can I call you Gabe, or do you want to be called Gabriel? What do you prefer?
Gabriel, please.
Gabe, all right. Gabe, what would you think about if I were to ask you to answer 1C?
I was thinking about if it's an ionic or a covalent compound.
And it is a
Covalent compound.
covalent compound. Very nice, very nice, very nice. So therefore, it would be called.
Dinitrogen trioxide.
So remember, there's only one nitrogen.
Oh, sorry, my bad. I looked at
All good. Yep. So go for it. It'll be called.
nitrogen dioxide.
Yeah, solid. Absolutely. Jesse, would you like to have a go at 1D?
Is that dinitrogen tetraoxide?
Nice. Yes. Very good. Very good. Okay. So example 2 then. Indicate the formula of the following ionic compounds. Okay. Do you guys know how to do questions like this? Like where they give you the name and you have to write the formula out? Do you know how to approach it?
No.
For example, if I asked you gold, okay, you know what, let's go top to bottom. Calcium phosphate, okay? Do we know what we should be thinking about and then how that leads us to actually writing out the formula?
No.
No? Okay.
Yeah.
So when it comes to ionic compounds, they've told you it's ionic compounds. Remember, okay, the cations, okay, they have a certain charge, right? And the anions, they have a certain charge as well. The idea is you want to be balancing out the charges, okay? So calcium and phosphate, right? When calcium becomes an ion, what is it? When calcium becomes an ion, what does it do? Does it gain electrons, lose electrons?
Okay.
It actually loses electrons. Okay. Jesse, do you know why it loses electrons?
Because metals have less electrons in the outermost shell, and they would rather lose electrons rather than gain.
Absolutely solid. Yep, very good, very good. And so calcium, if you notice, is on the second, it's on the second group, right? It's on the second column. Okay. That means it has 2 of these extra electrons in its valence shell, and it just wants to pop them off. So eventually, because it pops off its electrons, right, it'll become calcium 2+. Okay, that's the ion form of calcium. Now phosphorus, okay, do we know which group phosphorus is in, or what it would look like as an ion, Jesse?
Group 5.
So therefore, it has 5 electrons in its valence shell, and it wants to do what to get full shells?
Gain 3 electrons.
That's right. So eventually phosphorus will become phosphorus 3-. Okay. Now, you have a number 2, you have the number 3. Okay. If I add these together, so 2 + 3 - what does it end up equaling, guys? Basically 2 + 3 or 2 + -3.
-1.
-1. Yeah, not a trick question, just year 3 maths. Okay. So clearly you can see that we can't just write CAP because that's not going to be a neutrally charged ion. Okay, there has to be a certain ratio of the calciums to phosphorus so that they actually make a neutral product at the end of the day, right? And so the way you do that is you just think about, very simply put, between calcium and phosphorus, what's the common multiple, or what's the HCM? Between 2 and 3, between the number 2 and 3, what's the what's the lowest common multiple, not highest?
1.
So 2 times what gives you 1, Gabe?
1. Sorry,
Okay,
2.
2 times 1
times 1.
gives 1. I think you guys are confused. I'll make this clear. I'll make this simpler. Okay, we've established calcium forms this, phosphorus forms this. Okay, now if I were to get one of these calciums and I were to bond it to one of these phosphorus, the total charge here would still be negative. Okay, I want this thing to be 0. I want this thing to be like, yeah, I want it to be 0. Okay, so the way I make it 0 is I have to get enough of these 2 pluses and I have to get enough of these 3 minuses. Okay, so that the overall shape, okay, so the overall like ionic ratio becomes 0. Would you guys say that this over here, what I've drawn, would you say that if I add up the charges, it equals to 0? So add them up, 2 plus 2 plus 2, minus 3 minus 3. Does it add up to 0? Yes, no?
Yes.
It does, it does, it does. So basically what that means is if I were to get, okay, if I were to get 3 calciums and I were to get 2 phosphoruses, then this entire thing would have a charge of 0, okay, which is good because that's what I want. I want to know the ratio of how much calcium and phosphorus I need to make a neutrally charged ionic lattice. Cool? Are we still unsure where this is going? We know where this is going? Yes, no, confused, not confused? Don't be shy, guys. Please respond. Yeah, all right, nice. Okay, so the goal of trying to get the formula for ionic compounds is to find, that highest common multiple, sorry, the lowest common multiple, okay, that will eventually, when you add the charges together, it'll just end up becoming 0. So that is why over here, okay, the answer to this will be Ca2P3, okay? Because if I get 2 calcium ions, which each will have a charge of 2 plus, and I get, sorry, I did it wrong. It's going to be Ca3P2, okay? So if I get 3 calcium ions, okay, which are each going to have a charge of 2 plus, and I get 2 phosphorus ions, which are each going to have a charge of 3 minus, and I put them together and I keep them in that ratio, if I keep expanding this block of ions, it'll always be neutral. That's what I want. So that's how I can find the formula for this ionic compound. Gold 3 oxide, okay? Do we know how to do this? Like how to find the ionic compound for gold 3 oxide?
No.
No? Okay. Do you understand why they put this in there, by the way? Do you know what that means, guys?
I don't know.
Okay. So in the periodic table, you have a section called transition metals. You probably noticed it. It's like it's that little chunk in between the tall ones on the sides, right? In that chunk, okay, there's no fixed valencies, right? The valencies can vary. So when they put this over there, okay, all they are saying is that, yes, we know that these transition metals don't have a fixed valency, but here's the valency in this case. So what we're saying is for gold, the symbol for gold was it AU, guys?
AG.
AG, I think it's silver. Jesse, okay, do you guys know what the symbol is for gold? If you don't, just look at the periodic table. Don't sit there like a vegetable. So we can move on. Thank you, Jesse. AU. Okay. So with AU, right? They said it's AU3. So what that means is there are 3 valence electrons in AU. So when it turns into an ion, it's going to end up becoming AU3 plus. Okay. And oxygen, we know that when oxygen turns into an ion, okay, what does it do? Does it gain electrons, lose electrons? What does it do, guys? Gains electrons, right? How many does it gain specifically, Jesse? 2, solid. So oxygen becomes 2 minus because it gained 2 electrons. Now, once again, we're here with the same dilemma. I know that if I just write this, AUO, okay, this is not neutral. I can't, so therefore this can't be the formula. This is still going to have a positive charge, right? So how do I go about trying to put them in a ratio, in a molecular formula where they are actually neutral? I have to find the lowest common multiple. Okay. What's the lowest common multiple between 3 and 2? The lowest common multiple between 3 and 2 is 6. Very good, Jesse. Thank you. So the lowest common multiple is 6. So that means if I want to make, so I want to end up with 6 plus charge, and I want to end up with 6 minus charge over here, right? So how many gold atoms do I need to make 6 plus charge? 2, right? So I get an AU, and I'll get another AU. Okay. How many of the oxygens will I need? I'll need 3 of them. So I'll get an O, an oxygen, I'll get another oxygen, and I'll get another oxygen. Okay. If this is my ratio, okay, so if this is my ratio of, a gold and oxygen, okay, then bang, then I'm good to go, because now the net charge of this ratio of ionic bonding is 0. So I know that if I want to write the molecular formula in the lattice structure of gold-3 oxide, it will just be, for every 2 gold atoms, there is going to be 3 oxygen atoms. Okay. So the answer to this one is just going to be AU 2O3. Does that make sense, guys? Yeah, does that make sense of how we're supposed to go ahead and do these ionic compounds? Thank you. Very good. All right. So next thing, atomic structure. Okay. I'm just going to look how we're going for time. So I'm on 20, slide 20, 60, about a third way through. Okay. So I'm running a bit behind on schedule. Okay. And there's a lot of content to cover. So what I want to do is, as I said before, I want to ask you guys if you're confused with the concept or not. So the atomic structure, right? Is there anything about the atomic structure or any of these definitions that you guys aren't already sure of or aware of? Nope. Okay, moving on. What about here? Do you guys understand the Rutherford model and the Schrodinger model? Do you know what they are? No? You do? Okay. Sorry, I just saw a yes, a no, and a yes. Was there a no for this page? Or is it no, there's no issues? And yes, we understand everything from the Rutherford model and the Schrodinger model. Is that correct? Yep, no issues for this. Gabe, by the way, if you are there, okay, and you just want to, don't want to turn your mic on, you can just pop in the chat if you're having an issue or not. Okay.
I don't really understand the Rutherford model there. And
Rutherford model. Okay, if you're not sure about something, Gabe, I would like you to say it like up front. I don't want you to wait, because I'm going to be speeding through like this, right? So if you don't say it in time, you might miss it. You might not get that explanation. So yep. So just let me know like up front. Rutherford model.
Okay.
What is the Rutherford model? The Rutherford model is this one. This one to be. Okay, this is called the Rutherford model. Still, what exactly is the Rutherford model? It's a model that states that you have a nucleus. The nucleus has protons and neutrons. Okay, you have actually, this is not called the Rutherford model, guys. There's a bit of an error in these slides. Rutherford model basically states, it doesn't necessarily look like this. This is the Bohr model. Okay, the Rutherford model states that you have a nucleus, okay, and you have electron shells on the outside. Right. So here you have some electron shells. So you have an electron shell, and you have some electrons on the outside. We don't know how many, and you have a positively charged nucleus. Okay, this is the Rutherford model. All right. That's pretty much it. They don't differentiate between protons and neutrons, and they don't differentiate between energy levels. Okay, and that's eventually why Bohr came up afterwards, and he added some additions, and he added some things that are a bit more accurate. Make sense, Gabe?
Yes, thank you.
Oh, good. Okay, lovely. Moving along. So this is once again the Bohr model. Okay, so this isn't the Bohr model entirely, because do you see how, so if I play this animation, guys, okay. Sorry guys, just give me a second. Okay. Okay. So if I allow this animation to play, which would be very nice if it did, doesn't play, never mind, don't worry about it. Or does it? Yep, doesn't play. But basically what's happening is we're just showing you, okay. There are some animations in this file, okay? When you send your email through, you get the PowerPoint, you can play the animations, right? But basically all we're really showing you is the Bohr model here, right? The Bohr model has the nucleus, has the protons, has the neutrons, has the electrons, and the electrons, okay, as you can see in this little picture, they are orbiting around the nucleus. Now, the only difference that I want to make is in a textbook standard, the Bohr model is exactly this, but the electron shells on the outside, they're not in a 3D manner. Like they're not rotating one at this angle, one at that angle, one at that angle. They're all just rotating like on a 2D flat plane. So you have your positive nucleus and you have all of your electron shells just rotating like the rings of Saturn. Okay. Moving along. So now this diagram was an animation of Schrodinger's diagram. Do we know what Schrodinger's diagram is, guys, by the way?
No.
Jesse, do you know what Schrodinger's diagram is? No, okay. So Schrodinger's electron model basically states that there aren't really like orbits. You know how in the previous models we have like a nucleus and then orbits, right? Schrodinger's model states instead, sorry guys. Schrodinger's model states instead that there are areas around the nucleus. Okay, so for example, the first two electrons on shell number 1, okay, the first two electrons, right, they're going to be encompassing a sphere-like area, right? You're going to encompass a sphere-like area. So there is an area around that first nucleus, okay, where the electron is not necessarily going, it's not going in circles. What's happening is the electron is traveling like this. Does that make sense? Like it's traveling randomly, but it's going to be confined to that sphere-like area that I've just drawn. And that's why we call this an orbital. Does that make sense? Are we like understanding so far as I'm explaining this stuff?
Yeah, understand.
Okay, cool. Now, I won't go into too much depth, but basically, if we understand the concept that the Schrodinger's model, rather than orbits, gives us orbitals, which are areas, 3D areas, where electron spends most of its time, we have to understand that there's a few types, okay, that there is a few types of these orbitals. There's SPDF orbitals, okay? Now, these SPDF orbitals, right, they come in different shapes. You can see S is like a sphere, P is like an hourglass, D is like this, F is like that, okay? Now, you don't necessarily need to memorize or remember the shapes. What you need to memorize and remember for your exams, okay, not this one, is this thing, this table over here, okay? So how is this table relevant? Like, how am I supposed to use this? What exactly do I want you guys to memorize and understand? Let's say we get an element like oxygen, okay? How many electrons does oxygen have, guys?
8.
Okay, it has 8 electrons, very good. So what I want you to remember is that each of these subshells, okay, they hold a certain number of electrons. Do you see how it says 2 electrons, 6, 10, 14 electrons, right? So each of these subshells, they hold this many electrons. Now, you still have your levels. You know how like in the Bohr's model of the atom, or the Rutherford's, not the Rutherford's, but the Bohr's model of the atom, you have your nucleus, you have your energy level 1, you have your energy level 2, you have your energy level 3, right? Just imagine that in a 3D space, but you can have like S here, SP here, SPD here. Like you have shells within the shells in a 3D space. That's how I want you to imagine it. And so because you have shells within, so you have subshells within the shells or the orbitals, and you can fit a specific amount of electrons in each of these, that's what gives the limit of how many electrons you can put in each energy level. So when it comes to an atom such as oxygen, which we know has like 8 electrons, right? I want to know what are the subshells that fit onto an oxygen-like atom. And the way I do that is I follow this little diagram. It has a specific name. I have forgotten what it's called for the time being. But if you look up this SPDF arrow diagram, you should be able to find it. You need to have this memorized, okay? Because you're going to need it for your exams. So how this is going to work is, I know that all the S shells, they can hold up 2 electrons. I know the P can hold 4, D can hold 10, F can hold 16, okay? I know that oxygen has 8 electrons. So I'm going to follow the arrows until I fill up the shells, right? So let's get to this. So I know oxygen will have this shell, that's 2. Then I start at the next arrow. I follow the arrow, it'll have this one, that's 4 electrons. Then I'll follow the next arrow, 4 plus 4 is 8, okay? 2, 4, 4, yeah. Wait, I feel like I've done something wrong. Yeah, I've made a mistake. So everything is okay for the time being, except that this should be 6. That's my bad, 6. So do you see how, because oxygen has 8 electrons, right? The subshells that it's going to have, and I follow the arrows to figure that out, is it's going to have the 1s, the 2s, and partially fills up the 2p, okay? So the SPDF notation for oxygen, I'm going to write as 1s, and I'll put 2 because there's 2 electrons in that shell, 2s, 2, and then 2p, 4, because there's 4 out of the 6 potential electrons that 2p shell can hold. Now, if you're wondering what the heck is all of this, how does this make any sense? What is SPDF? Remember how we said the S, the P, the D, and the F, they have certain shapes. So this diagram allows us to first figure out what those subshells are, and then it then allows us to visualize, right? Then allows us to visualize the oxygen nucleus, okay? And there was the notation was 1s, 2s, 2p. That means what it looks like is it looks like this. In real life, it will look like, okay, that's 1s, right? And then there is a 2s, okay? And then there is a 2p. Okay, so I've tried to draw the areas in which electrons will be spending their time in the Schrodinger's model based off that SPDF notation stuff. I know it's a lot to take in, okay? You can watch this recording again. You can watch some YouTube videos as well. They should do a very good job at explaining this stuff. Does that make sense, guys?
Yes.
Yeah. Okay. And so if I want to do a question such as this silver, okay? How many electrons does silver have, guys?
79.
Okay, I probably don't want to do 79. Let's just do, sorry, is it 79 or is it 47?
Sorry, 47 almost.
47? Let's do sodium. I feel like sodium there's less electrons. How many electrons does sodium have, guys? $11. Okay, so I'll fill up my table until I hit 11. So I get this, okay, it's 2, 4, 10, and then 1 from here, okay? And do you see how I'm following the arrows? Like that's how I go to fill up the subshells, right? So the sodium notation would be 1s2, 2s2, 2p6, and 3s1. And that's how I get my 11 electrons. And then I can choose to draw it, or I can choose to just leave it as it is, but this is the SPDF notation. Okay, cool. Let's move on. So now, example 2 and example, sorry, there's only 2 examples. Those are related to what we've learned so far. Okay, let's go through the next concepts. Right, radioactive decay. Okay, are we familiar with radioactive decay and this graph over here, which is I think the nucleic stability graph? Are we familiar with this stuff? Okay. You want me to explain it a bit more? So no worries, Jesse. Especially half-life. Okay, so half-life is a different concept, but I'll explain half-life still. Is there anything about this in particular that you want me to explain a bit more? Like what exactly are you confused with? Oh, okay, so yeah, so this graph is in half-life. Gabe, do you know what this graph is about? Do you know what it's talking about, what it's showing?
No, sorry.
Okay. So All right, so basically this graph, this graph shows, I need to start from the beginning. Do you guys know what stability of a nucleus is even about? Like when I say an atom is going to be radioactive, do we actually know what that means? It's either yay or it's a nay. Which one?
No.
No. Okay. Okay. All right. So I want you to think of oxygen. Okay. So oxygen, we breathe it in the air. Can someone describe the nucleus of oxygen, please? The nucleus of oxygen, what's inside of it? Hello? Jesse, what's inside of an oxygen nucleus? One oxygen atom. If you don't know, you're not sure, just say not sure.
Not sure.
Not sure? Okay. So an oxygen nucleus has 8 protons and it has 8 neutrons. Okay. That's a nice ratio. It's about 1 to 1. Now that ratio doesn't always have to be 1 to 1 to be stable, but you don't see oxygen in the air like breaking down and turning into something else and losing its protons and neutrons and falling apart. When we refer to radioactivity, if something is radioactive, if the nucleus of that atom is unstable. And when we say unstable, all we mean is that it's likely for that to break down into 2 other substances. Does that make sense, guys?
Yes.
Yep. Okay. Now, there's a few factors influencing stability, as you can see over here. The neutron to proton ratio lies outside the belt of stability. I'll go over what that is with the graph. The ones I want you to focus on are these things over here. Okay. So you have excess neutrons. So either your nucleus has too many neutrons, or your nucleus has too many protons, or the nucleus itself is too big. So I'm sure you guys have heard of uranium, right? We know that uranium is radioactive, and we might not know why, but simply put, it's too heavy of a nucleus. Like there's not enough force in that nucleus of uranium to keep it stuck together. Okay. Yeah, so that's the nucleus, right? Now, where was it going with this? Size of the nucleus too high. Yeah. So it's just too big. It can't hold itself together to break down into like other substances. That's what makes it radioactive. Now that we have a bit of an understanding of radioactivity, I want to go through the graph. This graph is ridiculously simple. You're going to see it often. You're probably going to be asked in your preliminary exams to explain in a short answer question what to do with this graph. This is how you interpret it. So you can see on this axis over here, okay, there is they're giving you the number of neutrons, and they're saying not saying A to Z, they're saying A minus Z. If you don't know what that is, it means the mass number. A is the mass number minus Z, which is the number of protons. Okay, but yeah, the point is the number of neutrons, right? It's showing you how many neutrons exist, and then on this over here, it's showing you atomic number Z, which just means how many protons that exist. If you're on this line, okay, that means you have a ratio of 1 to 1, right? So you have a ratio of 1 to 1 on that line over there. Okay. Now you can see that there are some dots over here. Okay, some cool dots. Right? What are these dots? What do they represent? These dots represent all of the isotopes of elements that we're familiar with, okay, that are stable and they don't decay. As you can see clearly, this belt of stability, that's what it's called, it deviates from this 1 to 1 ratio. This line that's a 1 to 1 ratio, which means that you don't necessarily need to have a 1 to 1 ratio. Okay, you don't need to have it for stability, right? But you need to have it in a certain ratio. Okay, and that ratio is detailed in this graph. Now, the other thing that you'll notice in this graph is, do you see how it kind of stops over here? It's not really a straight line, but you get what I'm trying to say. Like it stops at around that point. And that's because everything that's over here, the nucleus is just too heavy to be stable anymore, and it's going to break down. Make sense?
Yes.
Cheers. Okay, now there's a few types of radioactivity. Are you guys familiar with these types of radioactivity? I'm asking because we'll skip through it just because we're falling behind on time. Okay, everyone's good? Cool. All right. These are some examples of how you actually like write out the decay happening. So if the question asks you, oh, demonstrate the alpha decay of this, right? You want to write it out in this fashion. Okay. I'll just focus on a little bit of the specifics because I know sometimes people get a bit confused with this. Okay. For alpha decay, you want to eventually have your helium atom out and you want to do your quick maths between the atomic number and the proton number and understand like what's being subtracted, and also make sure your actual symbols and your elements change. For beta, you're just taking out an electron, and the only thing that really changes is you have to understand that a neutron, right, broke down into an electron and a proton, and then the electron was fired. So that's why if you notice at the bottom, the atomic number goes up, even though you're only releasing an electron. Okay, and gamma decay is kind of useless because you just kind of add these on and nothing really happens, right? Sorry, you don't add all of them on. Normally you just add this stuff on, okay, and the symbol shouldn't change. The reason the symbols are changing in these examples is because gamma decay usually accompanies beta decay. So this and this usually happen together. That's why they've written these sentences like that. But you're not going to be requested to remember that. You just have to understand that if they ask you to show gamma decay and beta decay at the same time, you do a sentence where you consider the atomic numbers, you draw this symbol, and you draw your beta decay electron. Okay. Now, these examples, I reckon it's best if you do them with like when you get the resources and you send your email at the end. Okay. I'm just going to quickly go over periodicity. Right? Is this a concept that we're like quite familiar with, or? Yeah, we're quite familiar with this. Okay, all good. All right. Okay, if we're familiar with this, then we'll kind of skip over this. Right, these are just all of the trends shown in a pictorial format. Okay, the slides, you do have them as well. So if you want to look through the explanations of the periodicity, then you can do so for yourself. Right. The types of questions you probably get are these things, right? Like you get some multiple choice, you might get some short answer, but you have to explain with the trends why something has a certain property, okay? So for example, this question, you have both metals, both similar physical chemical properties. Then they're asking you, what is best explained? This is best explained by which of the following statements, okay? Can't be A, because metals have different properties, right? Could be potentially B. C has nothing to do with that because you have some non-metals that are low relative atomic mass. This is a pretty good explanation. They are in period 1 of the periodic table. But are they in period 1 of the periodic table? Is sodium and lithium in the same column for the periodic table? Yes, no? Guys, take a quick look, please.
Yes, they are.
They are. Okay. Okay. So because they're in period 1, right? So because they're in period 1, they're in the same space, and because they're in the similar space, they have similar properties, right? Now, can someone tell me why B is wrong? They have the same outer shell. No. This is a trick question. So when we said period 1, do we know what period 1 is, by the way, guys? It's not group 1, different thing. Do we know what period 1 is? It's the row, right? It's the row, okay? And the row has nothing to do with if they're similar. Sometimes it has something to do with if they're similar or not, but it's not a good answer, right? Because you can have a metal and a non-metal in the same period. Okay, so D is not going to be a good answer. So the answer should be B, right? But yeah, you can see that, these types of questions that you get, you should have a good understanding of where the elements are in the periodic table. And then as a result, you can explain the trends and whatnot. Does that make sense? I'm just going to take that as a yes. Okay. Ionic bonds, I have covered ionic bonds a little bit earlier in the ionic naming because we were trying to explain it then. Do you guys understand that it's to do with electronegativity. So electronegativity is just a fancy way of saying this atom or this cation, this anion has a certain tendency to attract electrons. So metals are cations and they have low electronegativity because they don't want to attract electrons, whereas chloride does. Okay, so these numbers over here, they're arbitrary, right? But they're just there to compare the electronegativity between them. Sodium doesn't want electrons, chloride doesn't want electrons, hence the size and the magnitude of the number. Okay, cool. So that explains also why sodium wants to eventually give its electrons to chloride, because it doesn't have a high electronegativity and then chloride does. All right. With non-polar covalent bonds, okay, there isn't really a difference in electronegativity as shown by this arbitrary numbers over here. Okay, so they pull the electrons equally and that ends up making them like, share the electrons between each other. For polar covalent bonds, so this is not ionic, this is stuff that is between a non-metal and a non-metal. Okay, you still have a difference in electronegativity, but the difference is still not that great, right? Because they're not that great, okay, they still kind of share the electrons, but the electrons are going to spend more time on like one area compared to like the other. Does that make sense, guys? And you can probably see that, I'm trying to represent that with my pen.
Yes.
So they'll stay more in the areas that are more electronegative. So for example, in this diagram, right? Chlorine is more electronegative than hydrogen. Okay, we can see that. So therefore the electrons will spend more time near the chlorine because chlorine is more electronegative. Electronegative means tendency to attract electrons. Make sense? Easy peasy. Alrighty. Okay, so that's polar covalent bonds. Very nice. Now, because of the difference in electronegativity, they're still covalent. So these two are still bonded covalently, but you have the manifestation of these two atoms having differences in how much the electrons spend time is that this becomes temporarily negative, this becomes temporarily positive. And because it's temporarily negative and positive, like sometimes it will become negative and sometimes it will become positive, it can bond to other atoms that are also polar and have your temporarily positive, temporarily negative thingies. So dipoles, not thingies. Okay. Are you guys familiar with Lewis dot diagrams?
No.
No? Do we know what Lewis dot diagrams are, guys?
No.
Okay. Okay. So Lewis dot diagrams, basically you show the covalent bonding between stuff. Okay. Now there is a way to do Lewis dot diagrams for ionic substances. Okay. And there's a way to do it for covalent substances. They look different. So I just want to make that distinction. Can somebody tell me in A, B, C, and D, what is the ionic substance?
I'm not sure.
Come on, guys. You should know what an ionic substance is from A, B, C, and D. The prelims are coming up soon. It's not a good look. Beautiful. Thank you, Urvi. Is that Urvi or is it, how do I say it? Urvi?
Hi, it's just Urvi.
Urvi? Okay, all good. So NaCl. So yes, NaCl is the ionic compound because there's a metal and there's a non-metal. Okay, so in a Lewis dot diagram, we know that the sodium, and the sodium has given its electrons to chloride, right? So we know that sodium has no valence electrons, right? And chlorine has, like a full shell. But we know that sodium and chloride have charges. So your Lewis dot diagram is going to look like this. Can someone tell me one of the from A, B, C, and D, which one is the covalent molecule? There's a few of them, so just choose one, please.
C.
C, yeah, water is a covalent molecule. So then we'll represent water like this. Oh no, sorry guys. Okay, so we'll represent water like this. Okay, so water, there's an oxygen in the middle. Okay, I don't know why that's there. Let me just get rid of that. Okay, so you have an oxygen in the middle. Just ignore this stuff over here. I don't know why it's there. There's oxygen in the middle. We know that oxygen forms single bonds with hydrogen. Okay, so this is what your diagram will end up looking like, right? Does that make sense, guys? So it looks different to the Ionic stuff, but basically in Lewis dot diagram, you just want to show the covalent bonds through the dots. Your screen is blocked from where you're drawing. Oh, okay. Here we go. Much better. Good. Very good. Okay. Yeah, nice. All right. So that's that. I'm just going to clear everything, clear pen markings. It's being very buggy, so I'm just going to restart this. Okay. So VSEPR theory. I'm going to assume you guys don't know what VSEPR theory is. We know what VSEPR theory is? We do, we don't?
No, we don't know.
Okay. So basically, if you look at these shapes, right? Okay. Dependent on how many atoms you have. For example, if you have, this looks like a CH4. Okay. You can see there is 4 of one type of atom and there is a central atom. That's the E, right? You're going to get different shapes of the molecule based upon what you have. Okay. So for example, if you have like H2S, right? And here you might have something else. Here you have H2O, okay? Right? I drew water wrong, by the way, guys. Water doesn't look like that. Water looks like this. Oh, never mind. No, it was fine. It was fine before. Yeah. But can you see how there is a certain ratio of like elements? There's a certain ratio of elements in all of the compounds that I'm writing next to these tables. Okay. If you can't see it, if there's a gray box covering it, I'll just move this. Yeah. But basically what's happening is when you draw your Lewis dot diagram, okay, sometimes we will have like a lone pairs. Now lone pairs are these things over here that I'm kind of drawing, right? Okay. So for example, oh, water is not the shape. Water is this shape. Okay. Water is this shape. Now you probably have to memorize which shapes are bent and which shapes aren't. Okay, or at least have an example for these. But otherwise, you can probably figure out the shape of the molecule by the ratio of elements in the compound and if it has any lone pairs when you do your Lewis dot diagram. Right. Now, based off that, you can tell if they have like these certain shapes, these certain orientations. Right. So if you see a black thing over here, like this black triangle, it's trying to show you a 3D diagram. Okay. So it's saying kind of looks like a tripod. Like this kind of looks like a tripod. That's what it's trying to say, right? But you can kind of see all of the shapes. You have the slides. You can Google image search these things as well to better understand them. The way that I would approach these, however, is I just understand that there is certain orientations, okay, for certain compounds, and they have these names of these certain shapes. That's how I would understand. All right. So they've given you a few examples to like work with. So they're saying, for example, NaCl. Okay, NaCl would probably look like linear. Okay, because it's just Na bonded to Cl. Right. H2S. Okay, so if I were to draw the Lewis dot diagram for H2S, it looked like this. Okay, pretty sure it's like this. Right, it probably looked like that as well. If I were to draw the thingy for ammonia, okay. I know that ammonia has a lone pair at the top, but apart from that, it just has hydrogens on the side. This shape you can see follows this pattern. So the pattern would end up becoming trigonal pyramid, right? But in the way that I'm doing this question, I know it's a bit rushed, you're not going to internalize it all right now. You can kind of review this. You can watch some YouTube videos. You can read over these resources that we've given you. You can Google image search these pictures again just to get a better understanding. But do we kind of have an inkling of an idea of how this is like working?
Yes.
Yeah. Okay. Easy. Moving along. Okay. Alrighty. So I'm up to intramolecular forces. Okay. But it is 3:30, okay? And at 3:30, we're gonna have a short 10-minute break because you guys have been going on for an hour and a half. We're also gonna have a bit of a handover in this 10-minute break, okay? And then in that handover, we'll try and finish off the rest of this by about like 5 o'clock. You guys understand? Everything good?
Yes.
Yep. From the stuff that we've covered so far, I know that some things we've had to go really quickly over, some things I've explained in a bit more detail. Is there anything else you guys would like to ask me before I hand over to the next presenter? Dipole and dispersion forces. You're confused between those two. Sure. So let's talk about dipole and dispersion forces. Do you know the difference and H bonding? Okay. So look, you have dipole-dipole bonding. Sorry, I don't want to do dipole-dipole. You have dispersion forces. Okay. Dispersion, right? You have dipole-dipole bonding. Okay. Dispersion is for non-polar molecules. Okay. Dipole-dipole is for polar molecules, right? And there is a subset, a subcategory of dipole-dipole called H bonding. Okay. This is basically dipole-dipole bonding on steroids. Now, the order of this is 1, 2, 3. And the reason I'm putting numbers is because if you have dipole-dipole bonding, you have dispersion forces as well. If you're a hydrogen bond, if you have hydrogen bonding, then hydrogen bonding is a dipole-dipole bonding. Okay. Yep. So hey, hydrogen bonding is dipole-dipole. So it's not like you have 1, 2, and 3. It's kind of like hydrogen bonding is dipole-dipole and you have dispersion. Yep. Solid. This is also for polar molecules, but only occurs in molecules that have a bond between the hydrogen and NO and F. These elements, right? That's how you categorize them and that's how you understand them. If you want to understand how they bond on a molecular level, dispersion works in the following. So let's just say we have HH. This is a polar molecule, and we want to understand why the gas hydrogen doesn't disperse like marbles, but does keep to itself when we disperse it in the air. It's because they have very weak intermolecular forces. See these electrons? We know these electrons are being shared. Okay, they have some electrons here. We know they're being shared as well. At certain instances, the electrons will be here and the electrons will be here. Do you see how now this electron is quite close to the nucleus of this hydrogen atom, right? And then this will happen instantaneously. Once again, like these two hydrogen atoms, they're going to have their electrons like moving around like roughly, randomly, spontaneously. And at certain instances, okay, they will have the orientation of the electrons in a way where you can have an electrostatic attraction between one molecule to the next. But it's very random and it's not going to happen often. It's going to happen 1 millisecond at a time, less than a millisecond at a time, but it's only going to happen for like 5% of the time that the hydrogen atoms are next to each other, right? Dipole-dipole is similar where you have polar molecules. So say you have HCl and then HCl. Remember that HCl is a polar molecule, which means that the electrons spend a lot more time at the chlorine than the hydrogen. So that means you're going to end up getting these like dipoles. Okay, so these are temporary areas of charge. They don't always exist there. They just temporarily exist, but they're a bit more frequent than the dispersion forces. So therefore, you're still going to get some electrostatic attraction between this because it's more frequent. It's going to be, because it's more frequent, it's going to appear more than the dispersion. It's going to be stronger than the dispersion forces. Now, with hydrogen bonding, it's the same thing as dipole-dipole bonding, but because you have a hydrogen and you have NO or F, they have the biggest difference in electronegativity. Biggest difference means that the electrons are going to be, towards the electronegative substance for a long period of time compared to all other than the two things that we've talked about so far. So that explains why you have that strength in between. Okay, that's why that explains the hierarchy of this strength. Does that make sense, guys? Easy. I'm going to hand it over to the next presenter now. Okay, so I'm going to turn the camera off. He's going to come in and discuss. I'll get him up to date with what's going on, and then we'll continue in a little bit. Okay.
All right, hi guys. Okay, is the camera on? Can you guys see me? Okay. Hello, I'm Rion. So I'm like the second presenter. I was supposed to be doing from module 3, but you guys only got up to what, slide 44, 128. All right. I think we're gonna have to speed through this since we only have like an hour and 20 minutes left. Are you guys in break right now? When did you guys start the break?
Ten minutes ago.
Oh, so okay. So can we just start instead of seeing through the rest of the break? Okay, cool. Because we are behind on schedule. So where did he end up on? Just intramolecular forces? Bonding?
Yes.
Am I going backwards or forwards? Okay. Okay, all right. Did you guys go through these examples?
No.
Okay. Have we gone through intermolecular bonding?
No.
So, okay, we're up to intramolecular forces, yeah?
Yeah.
Okay. So shall we start? Kind of, he explained it in the last 2 minutes. Okay. So intramolecular forces are those which are bonds, like proper bonds between between your, let me get the chat out of the way. Okay, so intramolecular forces are any force which holds together the atoms making a molecule or a compound. Intramolecular forces are those that are changed during a chemical reaction, whereas intermolecular forces, they're like the ones that cause physical, that happen during physical changes, when we change of states, or when it comes to like they're like they're not actual bonds, they're much more weaker. Whereas intramolecular forces, they include ionic bonds, metallic bonds, covalent bonds. Intermolecular forces have dispersion forces, dipole-dipole attraction, and hydrogen bonding. So ionic bonds are those between cations and anions. They happen when you have a electrostatic attraction force, because anions have a positive charge, whereas anions have a negative charge, such as table salt, you might know. Sodium being the metal and chloride being the cation, the non-metal, because what happens is your chlorine has such a strong electronegativity, it pulls the electron from the sodium, right? And it comes onto the chloride to complete its full shell, because we know all chemical reactions happen so that we can reach a more stable, product. In this case being table salt, which comes from sodium and chlorine ions. Metallic bonding is when you have one element. When it's one element, especially a metal, it's metal. When you have a metal and its electrons are delocalized. So what happens is you have the nuclei gathered in this lattice structure, right? So you have like a sort of, I don't have a diagram here. Wow, amazing. Okay, so you have a bunch of, okay, I can annotate, right? Okay, I can. So when you have, okay, this makes it much more easier. When you have a bunch of anions, so say you have a metal such as sodium again, we'll use sodium as the example. You have the proton or the nucleuses arranged in this lattice structure, and you have electrons in between these nuclei. Oops, that's supposed to be a negative. So what happens is you have electrostatic attraction force between the positive and the negative. That's what's holding the metallic structure together, the lattice structure. And essentially what the differences between an ionic and a metallic structure is that for metallic, you can actually mold it. You can bend it around. It's malleable. It's a very distinct property between ionic and metallic is that it's malleable. And the difference is metallic doesn't have a cation. It just has the electron that's holding the positive nuclei together. Whereas for an ionic, you have a cation that's holding it together and there are actual bonds. Whereas this is an electrostatic attraction force. This force is so strong, that's why it's called a metallic bond. Okay. Can I quickly rush through this? Are we good with this stuff? This is mod 1 stuff because we need to rush through. If I go at this rate, we're probably not going to go through a lot of the module 4 stuff. Can we actually skip this stuff? Yeah. Because I'll quickly rush through covalent as well. So what happens? Covalent is different to ionic and metallic in the sense that covalent shares an electron. Its valence, the valence electrons or number of electrons can be shared, and such that sharing causes them to hold on to each other essentially because of that orbit. Yeah, I'm just going to quickly speak through dispersion forces. Dispersion forces happens when you have temporary dipoles. I heard him saying temporary dipoles in the last second. Temporary dipoles because your electron, your cloud of electron, because of its random movement at some stages in your any time the electrons aren't perfectly spread out throughout your atom, and so it might be like coalesced in one area. That causes a negative dense charge in that area, and that can cause repulsion towards other electrons in a molecule in the vicinity, thus inducing that dipole, what's it called? That dipole charge. So it causes this polarity, and that temporary dipole causes them to attract towards each other. Similarly, a dipole attraction is where you have a permanent dipole, not a temporary one like dispersion forces, and that causes that electrostatic attraction force between the negative dense charge that's built up because of the electronegativity and the lack of electrons in the nearby molecule. Hydrogen bonding is where you have such a strong, it's just like he said, I heard him say, dipole attraction force on steroids, is where you have the negative dense charge is so strong that essentially it's considered to be as strong as a bond, like a covalent or an ionic bond. Though it's still considered an intermolecular force because it's only associated with physical changes. You don't really get these changes when you have a chemical change. So such as when you're, for example, when you're boiling water, water has hydrogen forces holding it together. When you boil them, you're essentially breaking these hydrogen bonds so that the molecules can disperse into the air and become a gas. All right, moving on. Oh yeah, just like I was saying before, this is just the properties of H1. I suggest you memorize these and sort of understand how these properties arise. So like I was saying, boiling points and melting points. Okay, so ionic and covalent, they have the highest boiling points, melting points, because they're actual bonds. Metallic, like I was saying, some of them, it varies because some of them have metallic, m equals to 10, theta equals to 1. Doing maths in here. Okay, anyways, so some, like I was saying, metallic has, it varies because you have electrostatic attraction force between your ions and your electrons. That causes, that electrostatic attraction force depends on the metal that's being used in the structure. Whereas for ionic, it's an actual bond, and that bond, when it's broken, it can actually cause shattering. That's why it's also brittle. Whereas metallic, like I was saying before, it's a sea of electrons, so it's very malleable. Covalent network is also bonds. When you have a bond that's broken, you can't actually fix it back together, right? It's broken, so you can't put it back together, therefore it's hard and brittle. And you can't change it, you can't twist it around. It's a fixed bond. If it's broken, it's broken. Metallic is a force. For metallic bonding, it's not a bond. Covalent molecular. Oh yeah, covalent molecular has low boiling points and melting points. Covalent network. Oh yeah, covalent network is you have like diamonds or like carbons where you have like a very large network because you have like a Tetris sort of structure, and those bonds have such like a 3D sort of lattice structure, and that causes it's very hard to break through all those bonds, thus giving it a very high melting and boiling point. Okay, metallic bonds, ionic solids are not. So most people tend to think that ionic solids are, conductive of electricity, but they are not, because they're actually you don't have electrons. So what electricity is, or what conductivity is through electrons. When you have a movement of charges, that's what causes electricity. In ionic bonds, you don't have that, because the electrons are fixed. They're fixed into the shells, right? So they're not actually moving. However, when you have ionic lattice structures that are dissolved into a liquid, it causes the ions to disperse, and these ions can now conduct electricity, because they themselves, when moving, like I said before, electricity is the movement of charges. These ionic bonds, these ions are able to move around in liquid and thus conduct electricity. Metallic bonding has electrons. So these electrons, like I was saying, they have a sea of electrons, and these electrons can easily be displaced by another electron. And since they can easily displace one another, they can keep moving along the lattice, the structure, the metallic structure, and thus conduct electricity. And the covalent structures, they have no charges at all. So you can't conduct electricity in either its solid or liquid state. All right, moving on. Intermolecular bonding. So PowerPoint, could you please? There's a box. Is it this box? Hope the whole. All right. Okay. Do we need to go through this intermolecular bonding?
No.
Okay, I'm going to move on. Can we move on from this? I'm pretty sure he went through VSEPR theory. I'm just going to move on from this. Can I move on? All right, let's just start with, since we're very low on time, we only have like an hour and like 7 minutes left. Oh my God. All right, let's just quickly move on. Do we know what moles are? Yeah? Okay, let's move on. Do we know that 1 mole is equivalent to 6.022 times 10 to the 23 molecules? It's in our formula sheet as well, right? So it's just mass over molecular mass. Do we know where to look for molecular mass of elements? Where do we look for it? Yeah, good. Periodic table. All right. 40 grams of water. We don't need to do this, right? This is easy shit. We can easily go through this, right? No need to do this? Clear? All right. Do we know what molar ratios are? And do we know how to balance equations? Yes, yeah. Who doesn't know how to balance equations? All right, I'll take that as normal. Good. I'm moving on. Easy stuff. We don't need to do this, right? Okay, limiting an excess reagent. Are we all good with this, or do we need to go through this a bit?
Can you go through, please?
Okay, limiting an excess reagent. So consider, okay, look at these blocks here. Imagine if this is 1 mole, if each square represents 1 mole of A and B. Say I have a reaction, AB becomes C. If this orange one is 1 mole of A and each one of these squares are B, right? You can see that they have a 1-to-1 coefficient, right? So that means if 1 mole of A combined with 1 mole of B, we get 1 mole of C, okay? So that means how many moles are going to be left over of which one? B, right? We're going to have some of B left, obviously, because all of A is going to be used up by the time B is finished up. So, but yeah, so we're going to have, since there's, how many do we have? 1, 2, 3 times 4, 12. We have 12 of A, so that means 12 of B, since it's a 1-to-1. each mole is going to connect with another mole to create 1 mole of C. So that means we're going to have 12 of A gone and 12 of B gone. That's going to give us 1, 2, 3, 4, 5, 6, 7, 8 moles of B left, or 8 squares of B left. That's what excess is. In this case, A is the limiting reagent, right? Limiting. Whereas this one is excess. We're going to have 5, 6, 7, okay, 8 in excess. All right, that's what excess is. Just the same thing, excess, yeah. Okay, determine the number of moles of each reagent. Divide the moles, okay, so limiting and excess reagent. So how do we do this? If we are given 1.8 moles of H2 and 1 mole of O2, the first thing we need to do is determine the number of moles of each reagent. So they already gave the moles, great. Divide the moles with the reagent with a stoichiometric coefficient. So what we do is, since we have 1.8 moles, we can divide it by 2, right? And this will give us 0.9. 1 divided by 1 is just 1, right? So that means we have 1 mole of O2 and 0.9 mole of H2 for the reaction, right? So, all right, that's what they did. And then you can see that 0.9 is lower than 1. So that means there's going to be 0.1 left of O2. Do we agree? So that's in excess, whereas this is limiting. Do we agree? Right? And this is excess. Oh, wow, amazing. What was the point of me writing that? Okay, easy stuff. Do we need to go through one of these questions? Should I go through one or skip?
Can you please go through one?
Okay. Write the balanced equation for the reaction that occurs when iron chloride. All right, I'll quickly go through. So iron chloride is FeCl2, right? Since it says iron 2, it's mixed with sodium phosphate, NaPO4. And since it's 2, there's going to be 2 here. We have to balance the equation first, right? So this is a double displacement reaction. Oh, oops. Oh my God. Double displacement reaction. So FePO4 plus NaCl. We're going to have 2 of these, and FePO4 stays as it is. So if 23 grams of iron chloride reacts with 41 grams of sodium phosphate, what is the limiting reagent? So we can see 23 grams. Okay, I'm going to need a calculator here. 23 grams. We're going to have to do molar calculation. So M over MM. How many moles of iron chloride do we have if we have 23 grams of it? Who can do the calculations? Let's get a periodic table out for this. Just wait. Okay, so iron Fe is 55.85. So right now I'm finding the moles. I'm finding the moles of FeCl2. Since we have 23 grams, I'm putting 23 on top, M, and then the molecular mass, I'm using my periodic table to find the molecular mass. Okay, so 55.85 is the molecular mass of iron plus 35.45 times 2, right? 35.45 is the molecular mass of chlorine. Since we have 2 of those, we times it by 2, and that should give us, who can do it on the calculator? I'm going to quickly go grab a calculator. All right, so if I put that into the calculator, 55.85 plus 35.45 times 2, we get 0.1815 moles, right? So that means to completely react, 126.75 is a molar mass. Yep, I just put it all to the calculator once. Okay, so since we have 0.1815 moles of FeCl2, that means it's a 1-to-1 reaction. So that means we need 0.1815, the exact amount of moles of Na2PO4 to completely react with FeCl2. However, we have 41 grams. So we also need to calculate the amount of Na2PO4 that we have. So we need the same calculations. So, okay, I'm going to do it up here. N equals to M over MM. Our mass is 41 grams. Sodium is like 22.99, so 23 times 2 plus P. Phosphorus 30.97 plus 16 times 4. 41 divided by 23 times 2 plus 30.97 plus 64, 0.29. Yep, 0.29, 0.291. Okay, so we can see that 0.291 is greater than 0.1815. Since this is a 1-to-1 reaction, right? If we have 0.291 of sodium phosphate, we need that much moles of iron chloride to completely react all of that sodium phosphate. However, we only have 0.1815. So that means this is going to completely finish up before we can even finish this one, right? So that means this one's going to be in excess, whereas this one's going to be completely used up. Do we all agree? Yep. Okay, second, so limiting reagent is FeCl2, whereas our excess is Na2PO4. How much sodium chloride can be formed from the reaction part B? Okay, now we know which one the limiting reagent is, and we know which one is in excess. Which one are we going to use? Which moles are we going to use to find the moles of NaCl? Can someone tell me? The limiting one, right? So FeCl2. Since we have 0.1815, right? However, NaCl is a 1-to-2 reaction right here. So it has 2 moles, right? So it's going to be a 1-to-2. So we have to times this by 2 to get our N of NaCl. Do we agree? Yeah? So if we do that, we get N of NaCl is equal to 0.363 moles. Since it's saying how much, it didn't really mention whether it didn't ask for grams or moles. So we can just leave it as 0.363 moles. Okay. How much of the excess reagent remains when this reaction has gone to completion? So who can tell me how much is the excess? Anyone? No? Okay. It's just our excess minus the limiting reagent, right? Because this is going to completely use up. This 0.1815 moles is going to completely use up. Since it's a 1-to-1 reaction, that's how much of Na2PO4 is also going to be used up. Since we have 0.291 of Na2PO4, that's how many moles we have, we can simply just minus it, right? 0.291 minus 0.1815, and we get 0.1095. Yeah. And that's going to be 0.1095 moles. That's how much excess we have. Are we good with this? Yep. All right, moving on. Do we need to do this? Example 3. How many more examples are there? Example 4. Should we do example 4?
Yes, please.
All right, we'll do example 4. Heating together the solids NH4Cl and calcium hydroxide can generate ammonia. Aqueous CaCl2 and liquid H2O are also formed. If a mixture of 33 grams each of NH4Cl and CaOH2 is heated, how many grams of NH3 will form? Okay, so our reaction. It already gave us the reactants and the product. So we have NH4. Ooh, why is it like that? NH4Cl plus CaOH2, we get the product CaCl2 plus H2O. So is it balanced? Wait, aqueous here, if you need to get the solids can generate ammonia. Oh, okay, and it produces ammonia. Okay, so it has three products. Is it balanced? NH4, H2, 4 plus 2, 6. It's not balanced. We gotta balance it. Fun times. Okay, so we have H2O and H3. Which one are we gonna mess around with? Does anyone know how to balance this? Okay, I'll give it a shot. So we have chlorine 2. So we're going to have 2 here, since we have 2 chlorines, NH4. So that gives us 8 hydrogens, 10. So I'm going to assume 2 here and then 2 here. So how many hydrogens do we have? 6, 4 is 10, 2 oxygens, 2 nitrogens. Is it balanced now? It's balanced, right? We have 4 hydrogens and 6 hydrogens, that's 10 hydrogens on the right. 2 hydrogens plus 8 hydrogens, that's 10 hydrogens on the left. 2 nitrogens, 2 chlorides, 2 chlorides, yeah, it's balanced. Okay, so now we can start. Always remember to balance, or else you're not gonna make any progress. You're gonna get everything wrong. Okay, if a mixture of 33 grams of NH4Cl and CaH2. So we have 33 grams of each. What's the first thing we do? Moles, right? So 33 over NH4Cl, so nitrogen, 14.01. I'm just going to put into the calculator all at once. It's 14.01 plus 1.008 times 4 plus 35.45. We get our molecular mass as 53.492. That should give us 33 divided by that, which is 0.6169 moles. Now, N of calcium hydroxide, right? Calcium is 40.08. So 33 over 40.08 plus 16 times 2 plus 1.008 times 2, which gives us 74.1. 33 divided by that is 0.44.53. Which one's limiting and which one's excess? Who can tell me? First of all, this is not a one-to-one reaction, right? NH4Cl, 2 moles of NH4Cl are being used for every 1 mole of calcium hydroxide, right? So that means, okay, so this is, I should have labeled it. This is calcium hydroxide, CaOH2, right? So that means for this to be completely reacted, right, we need 2 times this amount of NH4Cl. Do we agree? So that means we need 0.8906 moles of NH4Cl to completely react calcium hydroxide. Yep. However, we only have 0.6169. So what does that mean? That means this is going to finish first before we complete this. That means this one's going to be limiting. This one's going to be limiting. And this one's going to be excess. Do we agree? Yeah. So NH4Cl is limiting. How many grams? So now we can go to the question. How many grams of NH3 will form? We have 2 NH3. Since this is limiting, since NH4Cl is limiting, we're going to use the moles of the limiting to figure out the moles of NH3. Since it's a 2-to-2 reaction, it's essentially a 1-to-1 reaction. And since we have 0.6169 moles of NH4Cl, that means this will easily just be the moles of NH3 as well. And then to find the mass, we just times 0.6169 times the molecular mass of nitrogen of ammonia. So that will be 14 plus 1.008 times 3. So that's 17.024, your molecular mass of NH3, times the moles, 6. And that will give us 10.5. So that was like 17. 10.5 grams. Do we agree? Yeah, 10.51. Okay. What is the limiting reagent? I like how they asked that after. Which reactant remains in excess and in what mass? Okay, so we said this was limiting. We said this was excess, right? How much of, if NH4Cl is the limiting, how much of calcium hydroxide is going to be used to completely react the limiting reagent? Since we have 0.6169, if we just divide it by 2, we get 0.308. That's the amount of moles of the excess substance that's going to be completely used. Since we have available 0.4453 moles, we can just minus 0.4453 minus 0.30845, and that will be our excess. Do we agree? That's 0.13685 moles in excess. Clear? Oh, and you said in what mass? So, okay. We just have to times that by the molecular mass of calcium hydroxide. So 74.1, which we found before, 74.1. That's going to give us 10.14 grams. Clear? Moving on. Can we move on?
Yeah.
Okay. Percentage composition. Do we need to go through this?
No.
Okay. Okay, we can move on. Percentage composition is pretty easy. How about molarity? C1, V1, C2, V2. Are we good with this stuff?
Yeah.
Okay. Moving on. Gas laws. Are we good with gas laws?
Yeah.
Yeah? Everyone good with gas laws? Yeah? This stuff is pretty much just memorization. It's very easy stuff. You just memorize the gas laws, right? And you memorize the formula and the people's names. You have to memorize it. It will come up either as multiple choice or even like, oh, what is the contributions of Boyle's law? What is the contribution of Charles to chemistry? And then you just state the law, you just state what equation, and yeah, that's it. Not much. It'll probably be like a 1 to 2 marker. Not much problems there. But however, gas laws, when it comes to like the combined law here, are we good with this stuff? These questions can get pretty hefty sometimes. Should we go through one? Just one? Yeah? Okay, we'll just go through one. Let's go through, okay. How many examples are there? We'll go through the last one, I reckon. All right, example 2. Two flasks are connected with stopcock. Flask 1 has a volume of 2.5 liters and contains oxygen gas at a pressure of 70.93 kPa. Flask 2 has a volume of 3.8 liters and contains hydrogen gas at a pressure of 126.68 kPa. When the stopcock between the two flasks is open and the gas is allowed to mix, what will the resulting pressure of the gas mixture be? Okay. Do we know what to do here? First of all, which equation are we going to use? Okay. So we're using volume, right? And pressure. Temperature is going to be constant here. So we're using volume and pressure here.
Boyle's law?
Boyle's law? Yeah. So if we look back at Boyle's law, we have volume and pressure. P is equal to 1 on V. That means V1P1 is going to equal to V2P2. Do we agree? So what will the resulting pressure of the gas mixture be? Okay. So first of all, if we can find V1P1, it's going to be equal to a constant, right? V1P1 is going to equal to a constant K. So if we have volume 1 as 2.5 liters times 70.93, we get a constant value of 2.5 times 70.93, which is 177.325. Do you guys agree? That'll be our value K. .8. So when we open up the, the stopcock, what's our total volume going to be? 3.8 plus 2.5. Do we agree? 6.3, right? So if that's going to be our second volume. This question is a bit weird. Okay, you know what? I will revisit this question because even I'm a bit confused. What will be the resulting pressure of the gas mixture be? Okay, I will find solutions, and after I'll upload this and the solutions will be there. Is that okay?
Yeah.
All right. Anyways, we'll go through reactive chemistry. Where do you upload it? Like, how do we find it? I think it'll be emailed to you guys, everyone who paid for this. So they'll be annotated. So the other guy was supposed to go through mod 2. I was supposed to just do mod 3 and mod 4. So I have solutions for this. But yeah, I didn't go through any of this mod 2 stuff. So yeah. Anyways, like, okay. Reactive chemistry. Oh my God, we are so behind. Okay, let's speed run this. Do we know what chemical versus physical is? Chemical change, yeah? Chemical changes are essentially where you have bonds that are broken and bonds that are formed. That's what a chemical change is. A physical change, like before we were saying, it's intermolecular forces. When you're boiling something, you're not actually breaking any bonds. You're just causing those intermolecular forces to break up. Since they're not actual bonds, it's not a chemical change, okay? Moving on, easy stuff. Signs of chemical change. So when we have a chemical change, new substances occur, right? We get new products. These products something will cause a change, right? In our properties. That's what happens. When we have initial substances, our reactants, becomes our products, there'll be new properties. And the arising of these new properties will cause a physical change. So these changes can be like an odor, it can be the production of a gas, it could be the precipitate. Usually when we have the formation of a precipitate, we have the changing of a color. We can have a significant temperature change. So like it could become colder or it could become warmer. All right, can we move on? Production of a gas, production of an odor. So when we have an odor, we can assume that it's to do with a gas. When there's a gas, usually there's a smell. All right, so these are all indicators that a chemical change has occurred. All right, moving on. All right. They didn't put the format in. Okay, so a synthesis reaction forming a single compound. Do we know all these reactions? Synthesis, decomposition, combustion, and precipitation?
No.
You don't know? Okay, Which one do you not know? Do you know synthesis and decomposition?
No.
Okay, I'll just quickly write them down. So synthesis is just you have one reactant and another reactant, and they combine to form a combined reactant, like a AB. So in this case, you have A and then B, and it becomes AB. It's like you have H2 plus O2, and then you get H2O. You have to balance the reactions. But that's a synthesis reaction. Decomposition is the opposite. You have AB becomes A and then plus B. It's like when you have electrolysis of water, your H2O just breaks up, you get H2 and then O2 gas. All right, combustion. Combustion is just your reaction with O2. You have some fuel, so say CH4, and then you get the products CO2 plus H2O. However, this is when you have O2 in excess. When you have a limiting one, you have an incomplete combustion. So you can get products of carbon plus carbon dioxide plus H2O. Either one works. Whenever they give you a question regarding incomplete combustion, you can include either carbon or carbon monoxide, but you have to include at least one and not include carbon dioxide. That's if they tell you to do incomplete combustion. Okay, a precipitate reaction is just a double displacement reaction. So you're gonna have, like, say for instance, H2SO4 plus say NaCl, and then you get NaSO4 2 plus HCl, right? It's a double displacement. So this one gets replaced by this, and this one gets replaced by this, and you form two new products. All right, and then usually it produces an insoluble compound. In this case, this is not insoluble, so I did not do a proper precipitation, but this is just a double displacement reaction. Usually when you have two reactants and they have ions, these ions will come together, such as barium sulfate even. So if we change this to, if we made this BaCl, this would be BaSO4, and this will be a solid. And that this will cause a color change. This will be a white precipitate. This white precipitate will indicate that a precipitation reaction has occurred. Can we move on?
Yes, thank you.
All right. Acid and base. Acid and base is just a neutralization reaction where you have the production of a salt, right? An acid is something that has a pH lower than 7, whereas a base has a pH higher than 7. And so you have a hydroxide ion that comes from the base, right? You get a hydroxide ion, and a H plus ion comes from the acid. These two come together and they produce H2O, and whatever cation and anion that you have, they come together to produce a salt. Okay? Acid and metal reaction. Okay, so acid and metal is where your metal dissolves in your acid and it produces sometimes it produces a salt or an oxide of your metal, right? It produces a salt, and then it also produces hydrogen gas. Since it's an acid, like I said before, you have hydrogen from within the acid, and that causes that hydrogen to come out from its ionic state as a gas. And you also get a salt here. An example could be like if you have HCl and sodium, right? And you get NaCl as your salt, like table salt, and you have H2, and you just have to balance it, which is this, this, and this. Do we agree? Easy stuff. Acid and carbonate. This is also a neutralization reaction. So a carbonate sometimes has a very slightly basic basicity to it, right? Whereas an acid is an acid, right? So it has H plus. And so that is essentially, it gets neutralized by a carbonate, and your product will be carbon dioxide, right? You get carbon dioxide, you get H2O, and you get a salt, just like the salt from neutralization reaction. You get your H2O, which is the same, but since you're using a carbonic base, you're gonna get a carbon dioxide, right? Are we cool? Cool with this? Moving on. Metal and oxygen, metal and water. So example of a metal and oxygen. So by the way, with the redox stuff, we're going to go through that later either way, so it'll be fine. A redox reaction is where you have both oxidation and reduction occurring at the same time. So it's just a transference of electrons. So if you have a metal, for instance, Mg, right, the most common one, and you have oxygen, O2 as a gas, right? you're going to get the oxide, which is MgO, and you just have to balance it, right? Metal and water, it's roughly the same thing. H2O, you get MgOH plus hydrogen gas, right? Reactants. Cool. Are you good with this? The metal hydroxide, this hydroxide, again, if you remember, this hydroxide ion. This is what the hydroxide ion is. It comes from water. Water is made of H plus and your OH minus. So your H plus becomes your H2, whereas your OH minus joins with the magnesium to form your hydroxide. Cool with this? Moving on.
Yes.
Oh my God. Why is, okay. All right, moving on. Okay. Do we need to do this? I reckon you guys do this in your spare time, and then the solutions will be up, and then you guys can look at the solutions. Cool, yeah? I'm gonna move on. All right, detoxifying food. Do we need to go through this? This is pretty much memorization. This is in your, don't know. Yeah, this is basically just in your textbook. Do we need to go through this or skip?
Skip, please.
Yeah, all right, cool. Do this or skip?
Can you go through, please?
All right, all right. Okay, redox reactions is, like I was saying before, it's a transference between your reactants. So one of your reactants will be reduced, which means they will gain electrons, whereas the other reactant will be oxidized, and they will give the reactants, not the reactant, sorry, they will give the electrons to your one that's being reduced. So if we look at copper here, copper becomes Cu2 plus, and it gives away 2 electrons. That's oxidation. Oxidation is the process of giving away electrons, whereas reduction, in this case, the electron is joining up with the Ag plus, and that's taking the electron and it's becoming AgCl, Ag solid. So that's what reduction is, right? Oil's rig. Oh, okay. Reduction is gain. Oxidation is loss. Cool. Oil rig. That will help you remember what oxidation reduction is and to not mix them up. People do tend to mix them up because people think reduction is reducing electrons, but it's actually the gaining of electrons. It's the reduction of your oxidation state, which is a different thing. Okay, write the oxidation and reduction halfifications. Do you want me to quickly do this?
No, it's okay.
Cool. Okay, we can move on. All right, displacement reactions. So displacement reactions is, well, a single displacement reaction in this case is when you have a metal and another metal, and that metal, one of the metals is solid and your other metal is ionic, and that metal will displace this ionic metal if it's more reactive. So in this case, it's saying when a more reactive metal is placed in a solution that contains ions of a less reactive metal, the more reactive metal displaces the less reactive metal. So if we look at, for example, potassium, right? Potassium solid being added to a solution of AgCl, for instance, right? Since this Ag right now is in ionic state, right? Since it contains ions, it's ionic, right? If this is aqueous, whereas potassium is a solid, if this is stronger, it will displace this and this will be precipitated out. So you will get KCl and this will be ionic then, and your Ag will come out as a solid. So this is what happens if this is stronger. If this is weaker, this reaction will not occur. If this was reversed and Ag was trying to displace K plus, it would not occur because potassium is a stronger metal than Ag. Okay? So what happens here is that it's a redox reaction. So your electrons, since this is right now in its ionic state, that means it's been reduced, it's been oxidized right now. It's in an oxidized state. That means it's lacking the normal electron. Its valence electron is lacking. So what it does, it gains an electron from the potassium, which is so really reactive, right? We know that potassium is one of the most reactive metals out here. Its ionization energy is very low. That means it can easily be ionized or oxidized in this case, right? And the Ag plus has high electronegativity in comparison to potassium. So it will take this electron and become Ag solid. It will become a solid. It will take this electron. So that is the process of silver being reduced and potassium being oxidized. Are we cool with this? Okay, moving on. So, like I was saying, potassium is at the top. Reactivity increases. So it's saying the higher you are, the more likely you're to undergo oxidation. So what is oxidation again? The removal of electron, right? Like I was saying, its ionization energy is very, very small for potassium. So it's very easy to remove one of its electrons and it will undergo oxidation the easiest in comparison to like this or these ones at the bottom. So yeah, these are more likely to go, actually no, since these are all negatives, when you have, these are all metals are all more likely to undergo oxidation. When you have non-metals like chloride, you'll see they'll have a positive voltage here. It's because they're more likely to go undergo reduction. They're more likely to take, we know that non-metals in ionic, what's it called? We know, what's it called? Ionic salts, right? Salts, right? I was trying to get the salts. So you have cations, right? They're more likely to take the electrons from the metals, right? It's because they're more likely to get reduced. Whereas the metals, they're more likely to undergo oxidation because they want to get rid of that electron to have a full shell. Same thing here. So in this case, your reactivity increases with your oxidation voltage here. So these voltages, they represent, it's like a numerical measurement of which one is more likely to undergo oxidation. All right, moving on. Determine whether the following, do we need to do this? No? It's just showing, we just go back to here, right? It's just showing, like I was saying before, with the this stuff, if potassium is more reactive, it would displace Ag. So they're just saying, they're just testing your knowledge whether you know if Mg would replace Ag. So to look for that, you can always, if you don't know which one's more reactive, you can always just look at your activity series and you can just see the ones at the top are more reactive, so they will always displace anyone that's below them. All right? Okay, cool. I'm just gonna move through. The student is testing metals, XYZ. Okay, do we need to do this? Okay, moving on. Okay, oxidation state. So the oxidation state is essentially like your valency. It essentially represents like a valency. So oxidation numbers are typically written in Roman numerals or regular. We will use regular numbers in this slide. So the oxidation number of a free element is 0. So a free element refers to not just an element, it could be a compound. Any compound that's at standard state. So for example, like Na solid, right? Na solid. Most people think sodium has a charge of +1, but no, it only has a charge of +1 when it's at its ionic state. When it's a solid, right? It's not charged. It's just sodium, right? It still has that one valence electron in its outermost shell. It hasn't been oxidized yet. That's when it has a +1 charge. So the oxidation state of this is actually 0. It's not +1. However, Na +1, right? When it's in an aqueous solution or it's at its ionic state, it has an oxidation state of +1. Okay? Hydrogen has an oxidation number of +1 when it forms compounds with nonmetals, except in metal hydrides, the oxidation number of hydrogen is -1. So we don't need to memorize that. We just need to know that normally, or most typically, hydrogen has an oxidation state of number 1, of +1, +1. All right. Oxygen, however, usually has an oxidation state of number -2, except in compounds with fluorine, oxygen has a positive oxidation number. Okay, we don't need to memorize any of that. We just need to know that typically, in the most typical scenario, -2 will be the oxidation state of oxygen. Okay, -2. However, when it's O2 gas, what is the oxidation state of O2 gas? Can someone tell me? Can anyone tell me? So oxygen gas, is this currently in like an ionic state? Or is it at a standard state? Has it involved itself in any reaction, or is it at standard state? 0. It's neutral, right? It's going to be neutral. It's going to be 0 because it hasn't undergone any change. It's at its normal, right? In the air, we have oxygen. It's not charged, right? It has no oxidation state. It's just neutral. Okay. However, when you have H2O, or if you have, oh no, even there it's -2. Usually it's -2. Where if you have peroxides, right? In peroxide, this is a very unusual case. You won't get cases like this. This is just for extensive stuff. When you have H2O2, this is going to have a net charge of 0. So if H has a +1, you're going to get +1 times 2, right? And if we let oxygen be X times 2 equals to 0, then we're going to get X is going to have a -1 charge. That's the only other case. When it's involved in reactions and where it's not in the typical state, right? It's in like peroxides, for instance, or in compounds with fluorine, that's when it will have a different oxidation state. However, that is a very extensive question or scenario. Okay. I'll do one of these. So determine the oxidation state of the element referred. So if these don't have charges on top, they're all neutral. If they don't ever put charges on top of something, it's neutral. Or if anything is at its standard state, it will be neutral. When I'm saying neutral, I mean it has an oxidation state of 0. However, that doesn't necessarily mean that the individual constituent elements within that neutral substance has an oxidation state of 0. They can still have a different oxidation state. So I'll just do the first one. HCl has an oxidation state of 0. So that means, and since we said that H typically has an oxidation state of +1, and they're asking us to find the oxidation state of Cl, we can do an equation, right? So +1 times 1 plus C. Let's make that X equals to 0. So what's that going to be? X equals to -1. Easy. Cl -1. That's the oxidation state of Cl. Should I do pH 3 as well? Or H3PO4? This one looks hard. I'll do H3PO4. So H3PO4 is neutral right now. So it's going to have an oxidation state of 0. We know that H has a +1 charge. Oxygen has a -2 charge, right? So we can form an equation. Since we have times 3, right? We have 3 of these. Our charge is going to accumulate 3 times. Plus, let's make this X, right? And then since we have 4 of these, we can do 4 times -2, which is -8. It's going to equal to 0, right? -8 plus 3, what is that? -5, right? Equals to 0. X equals to +5. Therefore, our charge is +5. Do we agree? Can we move on? Okay. Determine the oxidation states of the bolded elements. Which one's bolded? It's not even bolded. Should we do one of them? Or should we move on?
Can you please do one of them?
You want me to do another one? Okay. We'll just go to the final one then. Okay, CH4 plus O2 equals to CO2 plus H2O. They didn't bold any of the elements. Okay. However, oops. Oh no. What the hell? What is this guy watching? All right. CH4 plus O2 becomes CO2. Okay, they didn't bold it, but I can tell that O2 is being changed right now. How can I tell? O2 right now is in what? It's in a neutral state here. However, you can see O2, you can see oxygen here is going to have a charge of what? Who can tell me what the oxidation state of oxygen is in H2O? -2. But oxygen over here is, what is it? Neutral, right? So it's going to be 0. So it goes from 0 to -2. So can you tell me if it's being oxidized or reduced?
Oxidized.
Oxidized? Are you sure about that?
Sorry, reduced, my bad.
It's reduced. It's being reduced because the oxidation state is decreasing. If the oxidation state decreases, it's being reduced. However, if it's increasing, you're having oxidation. Yeah, so I know a lot of people mix this up because they mix it up with electrons. When your oxidation state is decreasing, it doesn't mean you're losing electrons. It means you're gaining a negative charge. It means you're actually gaining electrons. Do you see what's happening? You're gaining a negative charge. So that means you're actually getting more electrons, right? That's why reduced is when your reduction, this reduce is not reducing electrons, you're reducing your charge, which means you're gaining electrons. Do we understand? Yeah? Okay, I'm gonna move on. All right, collision theory. 19 minutes. Are we good with collision theory? Do we need to go through collision theory? No? It's pretty easy stuff. It's just memorizing. You need to know, you need contact, obviously. When you're having collisions, they need to collide, right? They have to make contact. Activation energy is they need to have the required energy, and orientation means they can't be repelling each other. For example, if you have a sodium, right? If you have NaCl coming against NaCl, you don't want the sodiums to be hitting each other. They will repel, right? They have a positive charge. They'll repel each other. You want the Cl to come against the Na, and that will cause a proper collision. All right, I'm moving on. Easy stuff. All right, do we need to go through rates of reactions? Honestly, you already have these long responses right here. This is a very nice long response. If you just memorize these or go through them and understand them, I think that'll be enough. So you guys can just we uploaded, you guys will be emailed this. You have all of this. So are we okay with this?
Yes.
Move on. Okay. Temperature catalyst, same thing. Okay, who wants to just quickly do this? Which of the following factors affect whether a reaction between two molecules occur? Everyone just like spam, like whether it's A, B, C, or D. Just multiple choice question. B? Yeah, that's all it is. Activation energy and molecular orientation. So just collision theory. Not much else to it. It's not molecular. Okay, it's not concentration. No, we didn't care about the concentration. No concentration. Temperature, we don't care about that. Those are what increase rates of reactions, but they're not necessary for a collision. Okay. All right, moving on. Okay, this is, who can quickly tell me why is metal Y more reactive than metal X?
It has a higher surface area to volume ratio.
Yeah, it has a higher surface area, right? Metal X. Whereas metal Y, half its powder is inside, so its surface area is more exposed to the reaction. So more of the reaction is occurring for metal X, whereas for metal Y, half the stuff inside is not being reacted until the top layer has reacted, and then slowly those will be reacted. And that's why it's going to take a much longer time. Do we understand? And then you have to relate to collision theory. So you're going to say, because more of, since the rate of reaction is proportional to the surface area, or the the amount of reactions or the amount of collisions going on all at once, since half the stuff in the metal Y is not exposed to the reactants, therefore they're not going to be in any collision, therefore it's going to have a slower rate of reaction. Or yeah, do we understand?
Yes.
Okay, move on. All right, drivers of reactions. We have 15 minutes to go through module 4. Okay, energy changes in chemical reactions. Exothermic reactions. Do we know what exothermic reactions are? Yeah. Okay, I'll just quickly explain it. Actually, I think there's an energy profile diagram somewhere. Okay, anyways, so exothermic reactions, well, chemical energy is stored in bonds, right? However, external energy is required to break these bonds. So when you have a reaction, right, you have bonds being broken and then they're being formed, right? Collision theory, the basis of collision theory. You have bonds being broken, bonds being formed. However, when we break bonds, right, we need to apply energy. Energy is required to break these bonds. Whereas when we're forming bonds, energy is being released, right? So if the energy of forming bonds is greater than the energy required to break bonds, you're going to have more bonds, more energy that is being released. And so that's going to be what an exothermic reaction is. So exothermic is when you have a net energy release, right? Endothermic reaction is the opposite, whereas you're going to need more energy to break the bonds than the energy that's going to be released from forming it. So your net change in energy is going to be positive, right? You're going to be applying more energy to the reaction from the external than the energy that's going to be released. Therefore, your system is going to take more energy inwards. Okay, that's endothermic. All right, dissociation of an ionic lattice in water. To break bonds, energy is required. That's what we just said. Overall, dissolution of an ionic substance is generally endothermic. Okay, yeah. So we should know this. Sometimes they won't tell you this, and you might get trick questions where they'll say they'll have like an equation, and it will be like dissolving like NH4Cl in water. So anytime you have an ionic lattice that's being dissolved, you're breaking bonds, right? When you're breaking bonds, energy is being released. Oh, sorry, energy is required to break bonds, right? You're going to have energy that's required to break bonds. That's why we heat solutions sometimes when we want to dissolve it, right? When you want to get a cup of tea, right? You dissolve your stuff and you have it hot, right? You have hot water. That's your energy. That's you applying energy to the system to dissolve it. Therefore, it's endothermic, right? So you have to deduce that. We have to memorize this stuff. That ionic lattice, when we're dissolving it, it's usually going to be endothermic. All right, moving on. Enthalpy. So enthalpy is your net change. Like I was saying before, your net change in temperature is going to be your enthalpy. It's not your temperature change, it's the amount of kilojoules per mole. That's what it is. It's the amount of energy that's released, right? So change in energy. I'm going to get a charge or something. Okay, so it's your energy change. So your enthalpy, right? It's going to be positive when you have, it's going to be positive when you have an endothermic reaction because your energy required to break the bonds is greater than your energy required released from forming bonds. That's when you have a positive enthalpy. A negative enthalpy is when you have an exothermic reaction, is when the energy required to break bonds is less than the energy required formed and released when you're forming bonds. Do we understand? Can we move on? I'm just rushing through everything. Just if someone has any question in the middle, just ask me quickly. Okay, activation energy and energy profile. So this you will undoubtedly come across a question like this. So your activation energy, like we were saying before, is the energy required for your reactants to overcome, right? They need to have that energy to undergo the reaction and to become the products. They need to have that, right? In collision theory, you need to pass that barrier of activation energy to have the collisions, right? To have those successful collisions. If you don't have enough activation energy, right? If you just have a minimal energy, they're just going to bounce off each other. You're not going to break any bonds and you're not going to have any successful reaction. So we need to break bonds. To break bonds, you have to have the reactants have to have the correct activation energy, the required amount of activation energy or more, right? And your enthalpy change, right, as you can see here, is just going to be the difference between your reactants and your products, okay? Make sure you label all of these when you're drawing out. This is exothermic, right? Why is it exothermic? Because your products, the energy required to form the reactants, right? To break the bonds of the reactants is less than the energy from breaking bonds, right? That's why you have a net negative enthalpy change. And therefore, it's going to be exothermic. I'm just going to write exo. And this is going to be endo because the energy required to the energy required to break the bonds is more than the energy released from forming the products. All right, so therefore you have a net enthalpy change of which is positive. Moving on. How catalyst works. Okay. What else do we need to go through? We have. Okay, can we skip catalysts? Do we understand how catalysts work? Catalyst is just anything that speeds up the reaction. Yeah, it causes an alternate reaction pathway, as you can see here. It lowers your activation energy, and therefore your reactants, they don't have to have a great amount of energy to overcome the hill to start undergoing successful collisions. A catalyst will decrease your activation energy so that you can have successful collisions earlier on in the reaction. And so what it does, the purpose of catalyst is just to speed the reaction up. All right, moving on. Specific heat capacity. So different substances have different specific heat capacities. What specific heat capacity is the amount of heat required to raise the temperature of 1 kilogram of that substance by 1 Kelvin or 1 degree Celsius? Okay, so some substances, you realize they have very low specific heat capacities, especially metals, right? They don't contain the heat well, right? They'll conduct it off really easily. Whereas if you have water is a very good, what's a good container of heat, right? It's not a good conductor of heat. It's a good insulator. It contains the heat. So it has a very high specific heat capacity, right? And the equation that goes with this is Q equals to MCAP or MC delta T, where T is your change in temperature, C is your specific heat capacity, M is your kilograms or the mass of whatever you're trying to heat up. Yeah, remember this mass refers to whatever you're trying to heat up, okay? And Q is the amount of energy, right? Heat is usually measured in energy or heat energy. Do you understand? kg or grams, it's in kilograms. You can see here, it's in kilograms. That it's honestly dependent on your C. So in your formula sheet, your C value, right? In your formula sheet, your specific heat capacity is per kilogram, right? So sometimes they won't have the 10 to, so we know the 4.18, are we all familiar with this? Times 10 to the 3. Sometimes they don't include times 10 to the 3, right? This 10 to the 3 represents your kilograms. If this wasn't here, right, it'd just be grams. Do we understand? Okay, so we need to focus on C. If they say, if you look at your formula sheet, it's per kilogram. If they don't have times 10 to the 3, then it's just grams. Okay. All right, moving on. Calculate the heat energy in kg. You need to increase the temperature of 500 millimeters of water by 50 degrees. Do we need to go through this, or is it pretty easy? No?
No.
All right, moving on. All right, calorimetry. All right, do we all know what calorimetry is? Do I need to go through it? No? No? Are we cool with calorimetry? All right, I can move on. I'm moving on. So if we know what calorimetry is, okay, do you want me to quickly do this one or should we move on? It's just one of those easy heat of combustion questions. Move on? Okay. Okay, bond energy. Wait, let's just see what we have left. Hess's law. And what's after Hess's law? Gives free energy. Oh my God, we have not. Okay, what do we need to go through? Which topic? Which one?
Hess law.
Hess's law?
Yes.
Okay. Do we need to go through Gibbs free energy? Okay.
Yes.
I reckon we'll go through Hess's law and Gibbs free energy. We don't need to do any of this energy or formation stuff, right? We'll just do one of these. Do we know how to, so Hess's law, essentially, right? It's just like your energy, law of conservation of energy. Essentially, it's just saying that whatever pathway that you take for a chemical reaction, the energy required at the end, right? Your total energy between the reactants and your products, doesn't matter how you get from your reactants to your products, whatever pathway you take, your energy change will always be the same. So in this case, you can see that this one is negative 110.5 kilojoules, right? You can see how they go from this reactants to this product, and then these react again to become this product. Whereas And then this again, oh, sorry, it goes all the way to here, right? Doesn't matter what pathway you take. Your energy change, if you add these two energy changes up, they will equal to this ultimate energy change. So that's essentially what Hess's law is saying, that it doesn't matter what path you take, what reaction steps that you take. If you have the same reactants, same products, the energy required from that reactant to this product will always be the same. Okay? Moving on. Hess's law. Okay, yeah, so do we know how to do these? I reckon we should go through one of these because these can be very confusing. Yeah, I'll go through it.
Yes, please.
Okay. So for these ones, it's essentially the same thing. So these are different reaction pathways that they use to sort of stimulate this sort of reaction, right? Because these reactions aren't always able to be done. So in this case, we need to find what the enthalpy change is for this reaction. All right, so we can see there's carbon here and there's carbon here. There's no carbon elsewhere. So we can see, since there's two coefficient here, we need to multiply this whole thing by 2. Do you understand? So we're going to have 2 carbon plus 2O2 becomes 2 CO2. And then this is going to multiply by 2 as well. So if we multiply this by 2, you're going to have minus 393.5 times 2. Your delta H2 is going to equal to minus 787 kilojoule per mole. Do we agree? Yep. Okay, so we can also see that there's hydrogen gas here, right? If we look in this reaction, there's no hydrogen gas, there is hydrogen gas, right? We can already see it's already in as the same here. Hydrogen gas is the same as here. There's the coefficient the same, it's in the products, we're fine with that. So we can leave H3 as it is. H3 is equal to minus 285.8 kilojoules per mole, right? Okay, now we can look at the final reaction. We can see that C2H2 is our reactant, our product. So we need to have C2H2 on that side, on this side of the equation. Do we agree? Its coefficient is 1 and the coefficient here is 1, so it's fine. We don't have to multiply by any numbers. However, we do need to reverse the reaction, so it's in the products. So if we reverse it, we're going to have 2CO2 plus H2O becomes 5 on 2O2 plus C2H2. What happens to our delta H? Who can tell me? Becomes positive, right? Right now it's negative. However, we know in this direction it's exothermic. However, if we reverse a reaction, it becomes endothermic. So it's going to become positive, 1299.5. Now, if we add all of these up, you can realize that our oxygens, if we add the oxygens together here, 2.5 is equal to 5 on 2, 2.5 as well. So we can actually cancel these out. The H2Os also cancel out. We can see that our product and also 2 carbon dioxides also cancel out. Now we can see that 2C plus H2 becomes C2H2. And then we can just sum all of our things together. Our enthalpy changes, we get minus 787, minus 285.8, plus 1299.5, and we get 226.7 kilojoules per mole. Do we agree? That's going to be our enthalpy change. That's Hess's law. This is honestly the maximum of Hess's law that you're going to get, type of question that you're going to get. Are we cool with this? Move on. Gives free energy. Yeah? Do we need to go to enthalpy of formation?
No.
Okay, cool. Moving on. Gives free energy. Okay, entropy. So do we know what entropy is? And do we know how it changes? Yeah? So I quickly want to go through the qualitative analysis of entropy. So right here, so entropy essentially it's a measure of the disorder, right? So if you have liquids versus solids versus gas, a gas has the maximum entropy, right? Your atoms are all over the place, especially if it's very hot. They're very excited, they're moving all around. Whereas if you have a solid, they're in a lattice structure. or not necessarily lattice, they're just in a solid, right? They're fixed, they're not moving around as much, and therefore your disorder is very minimal, your entropy is very minimal. So gases naturally have a much higher entropy than solids, and a liquid as well, whereas a liquid has more entropy than a solid only. So if we look at this, right, if we look at this reaction, we can see that the products have 3 moles and these have 2 moles, right? So that means our entropy is increasing because we have 3 moles here for every 2 moles. So that means, yeah, just essentially our entropy is increasing. Additionally, you can see that there's a solid here and there's a solid here. So essentially, and you're having a gas, you also have a gas here, right? And these liquids, so your entropy of your solids is roughly the same. The entropy of your aqueous solutions or your liquid solutions are the same. However, you have a gas here. This additional of a gas increases the entropy as well. It just shows that your entropy is definitely increasing. This is qualitatively analyzing how entropy is increasing. Do we agree? Do we understand this?
Yes.
Okay. You can, I've also, there's also a wrong response here, so you can always just look at this to understand. Okay. Oh, also, there is a equation. Where is the equation? Here. So this is the equation. So change in entropy is the entropy of your products minus the entropy of your reactants. Cool. So in this case, if we look at our products, it's just going to be 206. If we just follow the formula, it's just going to be 206 minus the entropy of your product. So it's just going to be 130.6 and then minus 116.7. Do we agree? Then whatever that is going to be your net entropy change. Yeah. Do we agree? Yeah. All right. Spontaneity and Gibbs-free energy. So Gibbs-free energy is essentially this equation, right? We have 2 drivers. So essentially, whenever we have chemical equations, there's 2 things driving spontaneous reactions. Those 2 things are your enthalpy and your entropy. If your enthalpy is increasing, it's most likely going to be not spontaneous, non-spontaneous, right? And if your entropy is decreasing, it's also most likely going to be non-spontaneous. However, that's not always the case because these 2 drivers, they're the drivers of the reaction. If one can be compensated by the other. If your enthalpy is very negative, extremely negative, and your entropy is slightly positive, that enthalpy change can compensate for that lack of positive entropy. And so it will make it spontaneous. Similarly, it's vice versa as well. If your entropy is very small, if your entropy is very large, your enthalpy change can actually be positive for the reaction to be spontaneous. So, and always remember, if this is positive, then it's most likely going to be spontaneous. Okay. If your H, however, is positive, it's not going to be spontaneous. It's going to be most likely going to be non-spontaneous, right? If your H is negative, then it's most likely going to be spontaneous. And also another thing is, so these are quantitative measurements of spontaneity, right? So if your Gibbs-free energy is less than 0, which means this has to be negative, or this is very negative such that it compensates for this positive enthalpy, then your thing will be negative and it'll be spontaneous. Okay. When it's roughly 0, then it's neither spontaneous nor non-spontaneous. It's at equilibrium, which you will learn in module 5 later on. When it's non-spontaneous is when Gibbs-free energy is positive. Do you understand? Okay. Ice melting is a change. Do you want me to, okay, let's go through question 3, example 3. Okay, ammonia reacts with ammonia hydrogen chloride. Calculate the highest temperature at which the reaction is spontaneous. So it's saying your Gibbs-free energy, your change in G, has to be less than 0, right? Spontaneity occurs when Gibbs-free energy is less than 0. This means delta H, right, minus change in, the temperature isn't changing. Temperature times the delta S. Oh yeah, also entropy is, like I was saying before, entropy is dependent on temperature. like I was saying before, when you have a gas, right? If it's very hot, like I was saying, your atoms will be very excited. So the more high the temperature, the more excited your atoms are, and therefore your entropy is going to be even greater, right? So that's another thing. Okay, back to the question. So we can see that delta H, so they're asking for the highest temperature, right? So temperature is going to be our variable here. We have to solve for temperature. We can see delta S is going to be negative. So we can put in brackets negative 284.8. We can also see this is joules, right? Another thing is we need to notice that entropy is measured in joules per mole per Kelvin, whereas enthalpy is per kilojoule per mole. Since this is in joules, how do we get this to kilojoules? Do we know? Does anyone know? It's times 10 to the negative 3, right? Yes, yes. Divided by 1000 or times 10 to the negative 3, same thing. Okay? So now we just made this into kilojoules. Okay? Put that in brackets. It's going to be less than 0. And we can have negative 176.7 as it is. And we can just continue. So it's going to be negative 176.7 times is positive. So you're going to have positive, and then 284.8 times 10 to the negative 3 times t less than 0. We can move this to the other side, and then you get t is going to be less than negative, becomes positive. So 176.7 divided by 284.8 times 10 to the negative 3. And what does that give us? 176.7 divided by 284.8 times 10 to the negative 3. And we get temperature has to be less than 620.44 Kelvin, right? Remember, it's in Kelvin. So that's the temperature at which the reaction is spontaneous. Highest temperature at which the reaction is spontaneous. So anything less than that, right, it will continue being spontaneous. However, if we go beyond that, right, our entropy, since our entropy is negative, right, since it's negative, it becomes very magnitudinally big, such that it overcomes this this negative enthalpy, and it will become inspontaneous any larger than this value. Do we understand? Yeah? No? Are we good with this? Yeah. Should we do one more, or are we good with this?
One more, please.
One more? Okay. I'll do this one. Calculate at what temperature this reaction becomes spontaneous. So again, spontaneous gives free energy. What does it have to be? Less than 0, right? So delta H minus T, change in S, less than 0. We're going to have change in H be negative 91.8 minus the temperature times negative 198 times 10 to the negative 3, since it's in joules again. All right, it has to be less than 0. And then same thing, T, if we move this onto that side, becomes positive, and then we're going to divide it by this. Since this is negative, it's going to become positive. So we're just going to have 198 times 10 to the negative 3 on bottom, and then 91.8 on top. And that's going to be 91.8 divided by 198 times 10 to the negative 3. 463.636 Kelvin. Do we understand? Easy stuff.
Yes, thank you.
Yeah. Okay. Anything else that we need that, well, we skipped through a lot. We definitely did. Anyways, everything else is still up on the slide. Do we have any questions or anything we still want to go through? Any questions? Any misconceptions?
How do we get access to the mock exam thing?
Sorry, say that again.
You know, I don't know. The other guy was talking about the mock exam and like the notes and stuff.
Which topic? Which question? What did you say? I didn't get that. Did he just die? Okay. Any more questions? Or are we all good? Anyways, this will be emailed to you soon. Riaz will email it to you guys. I guess that's the end. How many people do we have here? Okay.
Thank you.
What were you asking?
It's okay. No, and I figured that out.
Okay, all right. Okay. All right, see you guys. Thanks for joining. Thanks for being here. Did we all learn something?
Yes, plenty of things.
Okay, okay, good. All right, see you guys. I'm gonna end the meeting now. Bye.